Good afternoon.
Here we are. Another day.
Another day.
Great. Are we going to use this today? Probably not.
I don't know yet. You can move it outside.
I'll just put it right there. Oh, wow. Here we go.
Here we go.
And James is right parked outside there, so I'm sure he'll
Okay.
in a second. Yeah, well, the last class was great.
We're good.
That was awesome. I'll jump over here and see it.
Just arrived.
Sounds like it. There he is.
Arrived. You have a rhythm.
How's it going?
Good. Anyway, this box here is our leftover box, so after any experiments, all the components that we don't even throw it in there, and then
Okay.
it's a community
That would be a
grab box. So
excellent. Oh, good.
it's most of the price of parts is sorting and organizing them, you know.
Right.
Yes, I bet. Especially meeting those resistor colors.
So, how was your weekend? Weekend? I know it's only 2 days.
Yeah.
2 days.
Midweek. Yeah. Pretty slow around the office, actually.
Yeah?
Yeah. The weekend was crazy, but last couple of days seems like we fixed most of the snow issues.
No, no.
Well, Bettles is still down, but it's just Bettles.
Bevels.
I have a friend who was stationed at Battle for 9 years, worked for the
Oh, yeah.
FAA.
Nice.
Wow.
It's a beautiful place.
I don't know why it's central to anything, though.
Right.
I mean,
Pretty much just a hunt camp at this point.
Is it?
It used to be a village, but then The village moved 5 miles down the road. What do they call that now? Edwards? Or something. Nelson Village or something like that. But it's just 5 miles down the river. And everybody migrated down there because better water or something.
Better water? Okay.
So Bettles is pretty much privately owned by the lodge now. So mountain area, kind of like Shoshana.
You guys are still maintaining all that, huh?
Oh yeah. Every village north of Campbell is mine. So.
Wow.
And actually a couple south there, because on the east side of the state, by the Canadian border, I do all of those. By the
Great working on
Oh, okay.
towers up there in -degree weather. Right? That's
Well,
you, right? Or what?
I don't climb the towers. I work at the base of the towers and the base of satellite dishes. So.
When I worked at Eielson, we had get certified for climbing towers, and we had 2 slips. One was a pink one, one was a blue one, and I asked them, why do you have 2 of them? One for getting up tower, one for getting back down.
Yep. Yeah, I'm not real big on tower climbing. I've tried it a couple times, but when you get up there, it doesn't feel very stable.
I've been 400 feet, KJP, and
Yeah.
playing with that thing. Of course, I was a lot younger and a lot,
Yeah.
a lot younger and a lot stupider, right?
Right. Oddly enough, though, when I was an electrician in Kansas for a while there, I had to run a ring of lights around the top of a grain elevator. And the grain elevator was at its highest point pushing 300 feet. There were actually 2 of them, and there was like 250 feet to the top of each, and there was a catwalk across, so you could go from one to the other. And we were running the wire across the catwalk on these wire grids, and up there didn't bother me at all. But I was on top of, millions of tons of concrete and steel, and I was like, this thing falls over. That's a sign from God. Like,
Yeah.
I wasn't just one guy screwed up, tightening a guy wire or something like that. That's the tower, man. It's like, you get one of those guy wires not done correctly.
Well, I don't know if Kevin's going to be out here today, but anyway, we can get started. So last week, any leftover questions from last week? We had
I think it settled pretty good.
We were asking everything.
It was a little scrambled when I left, but it settled.
Right.
understand super heterodyne receivers and what the IF amplifier is for and all that kind of good stuff.
Yeah.
Okay.
Yeah.
I mean, I'm sure I could probably spend a month on each subject and still have
Right.
questions. So,
Yeah.
it's like,
Well, concentrate on the stuff that's for the license, you know.
yeah,
What
right.
did you say with the receiver? What kind of receiver? What did you say?
Super heterodyne.
Oh, yes.
Convert everything to an intermediate frequency. Okay, so we're going to talk about the other end now. We're talk about transmitters and how good a receiver is. Must have something to transmit. There's not much to listen to, so we'll start with. So we're going to start simplest thing of how to actually generate RF to start with, without any consideration of any information we put on. We just want to get the radio signal out there. So first thing we need to do is we need to start with some sort of an oscillator. So what is an oscillator? Well, an oscillator is anything that creates an alternating current. Now, back in the ancient days of radio, when they had long-wave transmission, they actually used alternators. There's one they fire up once a year there. It was built about 120 years ago, called the Alexanderson alternator, which is just an electric alternator with a whole bunch of poles, you know. And they ran on like about 12 kilohertz or something like that. And they ran into extremely long wire antennas, you know. So, but as you start getting up to frequencies that you can't do mechanically, then you have to start looking about electrically. And we demonstrated how we could just take a battery and a coil and hit it once in a while, and we get a damped oscillation, you know, which is kind of how Hertz first transmits his signals. And even Marconi did that, because Marconi was around before vacuum tubes were. So you have a lot of very primitive ways of rather effectively generating radio, believe it or not. So anyway, what we're going to do here is talk about a little more conventionally modern way of generating a signal. So the first thing we need some sort of an oscillator, any kind of a generator. Now, normally what we use is we use an amplifier with some sort of feedback. And I showed you that receiver we had there that we actually use feedback in for a receiver. But in this case, we're using it to generate a signal to transmit. So we generate a signal, and ordinarily, typical solid-state oscillator, the RF output is going to be on the order of milliwatts. So not very much small amounts. So we have to amplify that with one or more amplifiers to get it fine up to the power that we need to transmit, and then we have to match it to an antenna somehow. So we have to convert our radio frequency amplifiers into some sort of matching system. So we'll talk a little bit about that. And by itself, without anything up to this point, we still have a valid transmitter. For example, a CW, or we call it continuous wave transmitter, used for Morse code. You're simply turning the transmitter on and off. So that's really all we need for a CW transmitter. And very efficient, very simple, and still very old and still very new. So CW still, if you have a shortwave radio, you can still hear a lot of shift-to-short CW operation using an 8 and 12 megahertz band. So anyway, that in that case, we can eliminate this part. This is a modulator, and in AM, what does a modulator do? What does a modulator actually mathematically? What's a modulator, an AM modulator, actually do? Or a mixer?
Combines frequencies.
Well, combines in what way, though?
Later.
No, it actually multiplies it. So you're actually multiplying one signal by the other. You have a little balance modulator here and create a nice AM signal there.
Right. So it multiplies it.
Yeah, it multiplies it. Yeah, so this is the signal here that you want to multiply by something, and the thing you multiply it with is your audio. And so that's continually changing throughout cycle. Well, let's talk a little bit about oscillators, since without an oscillator, I can't get much further. And take note of this.
So X is your modulator. It multiplies. Okay.
Now, any amplifier with positive feedback eventually will oscillate. It's kind of a thumb of the universe.
Any what now?
Any amplifier that has positive feedback is going to oscillate. Now, remember when we were building op amps, we had negative feedback. We had fed a resistor back into our negative point, and that adjusted the gain of the amplifier. And in all the examples we actually built, we actually ran that right to ground, so we weren't actually doing anything with a non-inverting input. If we were to move this around to this side instead,
Okay.
and move it around, and in general, what we want to do is we want to give some sort of a reference voltage here, but that's really not too important what's happening on this side. This is going to oscillate at some frequency. Well, the frequency it oscillates is going to be determined by some of the internal capacitance inside the device, and also stray inductance that we may have in the wire. So if we were just to do that, it would not generally oscillate at a useful frequency. Now, we can actually generate square waves with this, so we'll talk about that when we get into our digital circuits, how to use feedback to generate square waves. But what we want to do is we want to generate something that's semi-sinusoidal. Now, when you get to radio frequencies, a true sine oscillator is almost non-existent. So what we have to do is we start with as close to a sine wave as we can get, and then we filter it out, and we eventually get to a true sine wave later on. And we showed with the different waveforms here, when we built that tank circuit, you can put a square wave into it, it comes out a sine wave because of the filtering action of the, remember just sending pulses in there in the Class C amplifier. So any signal that's not a pure sine wave is a product of is a sum of the fundamental signal and then any harmonics that we have. So we show you could generate a square wave with a fundamental signal and all the all the odd harmonics. And a sawtooth wave has all the even harmonics. And then an infinitely narrow pulse, like the radar, it has all harmonics, everything. Not only all harmonics, but also has all possible sums and differences. So go a little more conventional here. Let's build a transistor amplifier, and you've all successfully built one in this class. So, so what do we got here? What's that? What terminal is that?
B.
B. Boy, which is the base. And what do we have down here?
E.
Emitter, right? And what's that? Collector. Okay, so what we can do here, we can put a tank circuit here. And a tank circuit, by definition, is any parallel resonant circuit. So we'll pick an L and a C value that
It's called a tank?
tank, right? So we'll pick some value of of L and C. Resonates at the frequency you want to transmit at. So pick something in the, keep it in the broadcast band, like 1 megahertz, okay? So we pick it at we pick some product of that, and remember there's an infinite number of different combinations of L and C that can give you that. And we'll talk about some of the finer points of what L to C ratio you want, but we'll just pick something that we know works. And let's say we have about 1,000 picofarads of capacitance, and then I'll leave it to an exercise to figure out how much capacitance that needs to, how much inductance we need to resonate with that. But let's say we've already done that. We can do that later. Now all we need to do is give some sort of feedback to this amplifier. Now, in this case, the amplifier's not going to do anything because until we put some voltage on the base, nothing's going to happen. It's totally off, okay? So what we can do here is we'll take a small amount of signal from our output and we'll connect it to our input. So what happens here when you first turn this on, hopefully we have a little bit of inductive kick on there, which is going to turn the transistor on. Once we have any current at all, the feedback's going to increase. So we'll start with a minuscule amount of current. As this increases, that's going to cause more current in the base to flow, which is going to cause more current in this flow. So then going all the way very quickly up to the point where it saturates, where you can't get any more current.
Okay.
And when that saturates at that point, we no longer have a change of current in their tank circuit. So the tank circuit is going to release that energy back out of phase. So when that does that, it's going to reverse polarity here, and then it's going to drive this base off. And then the whole process is going to repeat again. So
to drive the base off, it just turns it off.
Turns it completely off, and then the energy is stored in the tank circuit. And then as that recycles again, the second we're going to show the damped oscillation. Kick it once and it's going to keep oscillating.
Yes.
On the next positive cycle, it's going to come back through here, and cause the transistor to turn on again.
Wow.
And then the whole process keeps repeating infinity.
So that's on the tank circuit, the L, that's an inductor, and then what is that?
That's just a coupling inductor.
Inductor.
Remember the secondary inductor we had to couple some energy off, like the Taylor coil on that receiver there. It's just a second coil that's in proximity to it.
Yeah. Wow.
Okay, so that's just one way of doing that. That's one of the oldest means. It's called an Armstrong oscillator because it kind of strong arm the thing into working.
Right. Hopefully you're wondering even if it's been off for a long time, something will get started.
Generally, most oscillators rely on some amount of circuit noise to get it started. It doesn't take much. But
wow.
Now, any amplifier, the amount of feedback you need is only enough you only need enough to compensate for the circuit losses. So any amplifier that has a gain of more than one, it will oscillate. You get positive feedback. So you don't need a whole lot. And if you have an amplifier that already has a lot of gain, it's going to oscillate very easily. And when you have amplifiers with a lot of gain, it's a real problem not to have them oscillate. One of the big problems in generating and creating high gain amplifiers is making it stable so they aren't oscillating when you don't want them to. Of course, if you want it to oscillate 90% of the time, it won't.
Just the law of,
yeah, if you want it to oscillate, it won't. If you don't want it to oscillate, it will. So it's just life. Now, one of the problems in building an Armstrong oscillator like this is in order to make sure that it starts, we have to be very careful of the phasing between the primary and the secondary on that little transformer. And sometimes you can't really know until you try it and it doesn't work. Well, one of the revisions that will make a circuit where it's always going to be in phase is called a Hartley oscillator. And we haven't talked much about auto transformers yet. So far, the transformers we've talked, we actually have two separate coils in the induced field. Right? But you have a thing called an auto transformer where you only have one coil. Where you're reusing part of the coil here. So, for example, this could be an input signal between here and here, and there's your output signal between there and there. Have you ever worked with a variac? Do you use variacs at all? Is it just your line voltage?
Sounds very familiar.
Yeah, those are just auto transformers. So there's nothing that says the two coils have to be separate. They can be tied together. So you just depend. The turn ratio is going to be your voltage ratio. So you have 1/4 of the way up here. That is going to be a 4-to-1 step up or step down transformer. Well, we do that in a Hartley oscillator. So what we do here is we start with a transistor again, and all of these, by the way, were also accomplished in vacuum tube amplifiers as well. So what we do here is we have a tank circuit. And that's really all we need. Just has to go on the ground as well. And leave over there and tie that to ground. So when you first turn this on, and normally you will need to add a little bit of a kick here. And try it, and that's right over here. We were trying to make an oscillator work, so we had to play around a lot with this starting resistor here. But it doesn't take much. So usually on a typical, small signal transistor, maybe 100,000 ohms or something. It's just enough to make the transistor go slightly turn on very slightly. Not like the Class A amplifier where you want this all the way up to the point where it's half voltage at the collector. It's actually going to be operating what we call Class C, which the transistor can be off most of the time. So we just have to have enough circuit just to get things barely started. Now what happens when this first starts, we start drawing some current through the emitter. And since that point there is part of this auto transformer, it's going to step the voltage up going back to the base there. So this transistor is going to compensate for any losses that we have here. And because it's one coil here, you can't accidentally swap the polarity of half the coil. So this is what's used in your local oscillator in 99.9% of your AM radios. The local oscillator we use for the super heterodyne down conversion is usually a Hartley oscillator.
Wow.
And if this is variable, we can make this work at variable frequencies, right?
If the capacitor.
Capacitor, right? You can capacitor. So that's
right.
where your tuning dial is on a radio. Yeah.
Right.
Well, that's your Hartley oscillator. Well, it's a Hartley. There's only going to be a split coil there. Another variation, or I should say another type, but it's kind of complementary to the Hartley, is called the Colpitts oscillator. And you recognize that because that has a split capacitor. So we have a single inductor here. And then our feedback goes to a midpoint of a couple of capacitors here. So that's your basic. Now, see something here that seems a little odd, you might why won't that start? I mean, why won't it run? Even if we could start it, why won't that run?
Because the emitter goes to ground.
Well, it doesn't go to the ground, it goes to its midpoint, so it's kind of floating in space. There's no DC path. Okay?
No DC path.
So what you usually do is you have a very large choke here, which is many times the value you need to resonate, so it's nowhere near the resonant frequency. And put it there. So you give it some sort of a path, DC path to ground there. But it has to be far enough away so that doesn't resonate with that. So it's called a shunt-fed coal pits, and it's called shunt because you have the DC path is parallel with the actual signal path.
Sounds like my favorite term.
But coal pits, was that?
Sounds like my favorite term in the electrical world.
Oh, shunt.
It just sounds good.
Short circuit. So anyway, that's a coal pits. You always recognize coal pits because it has two capacitors. They're split capacitor. Now both these are, with careful design, they can be pretty stable. However, what happens if you make a coil out of any metal? What happens is the temperature gets warm, starts expanding, right?
Oh, yeah.
So every oscillator, unless you take special care, is going to drift lower in frequency because the coil is going to get larger. If you look at the formula for inductance, it's always going to increase there.
Even by just a tiny amount, it's going to.
A tiny amount, it can be huge amounts,
Oh,
especially
wow.
to get up to radio frequency. So yeah,
Right.
it's stuff you can't even measure with the finest microscope, but it's enough to change
Frequency.
Yeah.
Wow.
Part of it is because, and if you look at that equation for the inductance there, the inductance goes up as a square of the number of turns and a square, like you've got all these square terms, which makes things
Right.
happen a lot faster than you would think.
Mm-hmm.
Now, the capacitance also changes a little bit, but nowhere near as much. And one way they compensate for this is with a temperature compensating capacitor. Now, generally, as the capacitor expands, the plates tend to get apart because the dielectric gets fatter, so the plates are going to be lower capacitance, so they would drift up. But the plates also expand outward; they become larger in area. So that part tends to compensate for itself. They get farther apart.
I see.
But what does change is the actual dielectric material, not so much in an air capacitor, but in these ceramic capacitors or anything, the material itself changes.
Also
Very
changes.
temperature sensitive. So they can take advantage of it. They can use a certain type of ceramic that has the positive temperature coefficient, so as the inductance tends to expand and go lower in frequency, that decreases the capacitance as you go up. And then, so if you pick the right value of compensating capacitor.
Whoa.
That was a big job for, especially for amateur radio stuff, where we weren't crystal controlled, but you want to have a variable oscillator as stable as you could. So you spend a lot of time with temperature compensation, And so you turn it on and wait half a day, then like
That long?
Yeah.
Get it nice and hot.
Sometimes
then
sometimes it would never get into thermal stability, thermal equilibrium. And in case where you really need, like instrumentation, like a frequency counter where you're the reference there, you put the oscillator inside an oven and you keep that at a specific temperature. So
Wow.
I have a whole bunch of ovenized crystals here. So. Okay, so we mentioned that about the highest Q you can get with a free running tank circuit, just was about 200. Well, for a lot of applications, that's okay, but where we really need precise frequency control, it's not okay. So we do the next best thing, and which is actually a huge step above it. We use a thing called a quartz crystal, and I've got a whole bunch of them here. So I got a whole stash of these are hermetically sealed quartz crystals.
Are they?
HC6 type. These are FP243 military surplus, which you can take apart and see all the guts in there. So a quartz crystal is a slab of quartz between two capacitor plates. And the characteristics of quartz is when you apply a mechanical strain to it, it creates a voltage. And if you put a gold across it, it actually deforms the quartz a bit. So because of that, the quartz is...
If you were to like try to twist it?
Well, there's several different modes. Matter of fact, that's some of the main advancements they did in quartz figuring mode. There's There's a vibrational mode, which is probably the most common mode, where it actually suspends between two points and it wobbles back and forth.
Right. No.
There's a thickness mode where it gets fatter and thinner, so it wobbles thin that way. There's torsional modes. There's shear mode, where you start out with a trapezoid or parallelogram, and then it becomes more.
Huh.
You have two-side shifting like that.
Wow.
So every possible mode there is, a crystal will oscillate in. Some
It
more
will.
than others, but some are more stable than others. So
Oh, I see.
yeah,
And that
and then
produces a voltage
that's produces voltage. Yeah.
when it's
When
vibrating.
it vibrates,
Also,
so the physical vibration of the crystal is what actually generates a signal. Now, the Q of a vibrating quartz crystal is between 100,000 and a million,
Oh,
compared
wow.
to 200 for a coil capacitor. So
very specific.
extremely tight frequency.
And again, the reverse is if you pump voltage through it, it'll vibrate
Yeah.
at a very specific.
Right.
Yeah.
And let's see. Oh yeah, you can also get overtone modes where rather than wobbling in the middle, the crystal actually flexes like that. So that would be like, where's my handy dandy?
And how thin of a piece of crystal are we talking about?
We'll take one apart.
Yeah.
So here's a fundamental mode, and here's there's a second harmonic,
Right.
and
Third.
third harmonic.
Uh-huh.
Crystal can operate in all those modes.
Wow. So that would matter on the how high the voltage here.
No, it depends on what your feedback frequency is. Now, what reason you want to use the harmonic mode is in order to get a crystal thin enough to vibrate at the frequency you may want. That would be too thin.
Yeah.
So you use a thicker crystal but operate at
I see.
it's called overtone mode.
Overtone.
So
And we're still using this.
that's all we're using. I mean, these are. That's how you keep a microprocessor on time.
Right. This is the technology now.
The only thing that's changed is they're smaller.
They are smaller.
That's a microprocessor crystal.
Yep. How are they so small?
Just a lot of fine machines.
Still machine.
There's a great movie there. Since I'm on YouTube, I can't show it because I'm trying to get the.
Why watch that?
but I'll show it offline there.
Can't give all the secrets away.
Yeah.
Right.
Well, not because of that, because there's copyright stuff there. So,
Oh, yeah.
So,
It was the video you showed me with how the Army used to do
yeah.
You gotta see it, man, how they make these things. And to see them doing it smaller and smaller now,
Yeah.
I mean, that's really fine machine. That's like semiconductor wafer.
So nobody's come up with anything that's really better than the quartz crystal in terms of the precision of it.
And you said there's like one place that made it Brazil or something?
Well, that's where the quartz itself comes from.
Right.
Yeah.
And that's the best stuff in the world.
Yeah.
Nobody else.
Nobody.
Brazil. One country.
Is it just
One mine.
One mine.
like a purity?
Yeah, because of high enough Q for electronic grade. So
Oh, incredible.
that's one of the motivation for making the crystals smaller and smaller.
Well, yeah.
Right, so you couldn't just walk out to the White Mountains.
No.
Hopefully we're not running out, are we?
No, they've been able to conserve it with, again, using that. You don't have any big slabs of quartz crystal used much anymore.
Okay. That's incredible.
Now, since it has a property, we can draw and make an electrical equivalent of the actual quartz. Any mechanical device has a electrical equivalent, so the quartz is actually physically vibrating, but if we want to see what it looks like as an actual circuit.
Oh.
And let's see. So a typical let's say a 10 megahertz quartz crystal, on the order of one of those here. This would be the equivalent circuit of it. Now, what gives the circuit its incredibly high Q is this resistance in here, maybe a small fraction of an ohm, like 100th of an ohm or something like that. And this inductance here may be several henries. Now, several Henry inductor would be huge if in an actual inductor, but but it's a mechanical equivalent. So we're taking a thing that's physically moving and converting it to what that would look like if you had to actually build circuits. So if you wanted to synthesize a court using only regular components, this would be a few Henrys.
Yes.
I mean, 10 Henrys. I don't know, 0.0001 ohms, and then whatever passes. Now, this capacitor is called a holder capacitor because the quartz crystal by itself, there's no way of getting electric current through it because it's an insulator. You just can't attach the wires to it and make it work. So you have to capacitively couple to it. And then that capacitance also shows up as a parallel capacitance with the quartz itself. So that can alter the performance of the crystal, and there's tricks we can do that make it either go away or take advantage of that. But anyway, any circuit that would like something like that, like a high Q series resonant circuit, we can put a crystal in its place. So, since we know the crystal is already a tuned circuit, we can build an oscillator out of it. One of the simplest ones called a Pierce oscillator, where you just have a transistor amplifier again, and usually have a little bit of inductance there, and just have a crystal between there and there, and that in general will oscillate pretty easily by itself. Now it's not the best crystal oscillator, but most time it'll really work. And that little crystal tester right there is actually just a Pierce oscillator. Oh. Crystals good. So put a crystal in here. Oscillate, light.
Okay. Yeah. Wow.
Good crystal.
It's good.
It's good.
Would you explain the? Oh, okay. Wait. Would you explain is that where the crystal's being held?
Yeah.
What's in that? What is that?
Well, that is the crystal.
That is the crystal. It's just being held there. That's not a capacitor. That's not.
No, that's the symbol for crystal.
That's the symbol for crystal. Okay. And then that is a. And so there's a transistor here. Is that what you're showing?
A transistor here.
Is there a wow? Okay.
And you might need a little bit of a kick-starting resistor here too, just enough to get it going. But once it's going, it oscillates pretty strongly.
Wow.
That's our Pierce oscillator.
Yep. Before the movie.
Oh, yeah. His first career.
Yeah. Wow.
So, when we take a crystal apart, you saw the inside of one.
Oh, yeah. Now are they so small that you can't really handle them with your hand, or like in watches?
They're hermetically sealed, that's all put together by automation,
But these are big. These are kind of big. Yeah.
Proper screwdriver. Now, keep in mind that is spring loaded.
These are sealed.
Yeah, those are hermetically sealed.
Okay, and then this was just too small.
Yeah.
So, I mean, if you really open that up, is that? I think it's smaller than this, I'm sure.
That's about the smallest without custom,
Okay. But what about like in watches out of the quartz?
Yeah, those use slightly longer, skinnier one.
Oh, okay. I mean, I imagine handling these things, they get pretty brittle out, that thin and that.
Well, yeah, it's super paper thin.
Very.
So that's all.
Right.
Operated by, so you're on camera here, so you get that,
There you go.
looks like you know what you're doing there.
Just some random guy off the street.
Yes.
Here's a watch crystal.
Really? Okay.
You know, if that hasn't been apart in 70 years, you might have to encourage it.
Just don't point it this way. Oh. You need a. Well, there you go.
Oh,
Something to kind of, yeah, he's got something there. There you go.
Beefier blade there. Anything got it?
Got it. Just hold it. Oh,
There we go. Okay.
spring loaded.
Okay, so you pull the cover off, put that aside. And a little rubber pad. And there's a brass plate. Yep, and then there's a steel plate under that. And then there's another, then there's crystal, and the crystal's inside those two steel plates.
Holy crap.
So that's your little slab of quartz, and that actually vibrates. Now, if you look at the steel plate where you took it apart, you'll see the raised edges on the inside there.
Uh-huh.
It's suspended, they're about a 10,000th of an inch thicker there, so the crystal is actually suspended between them, so it can flex back and forth,
Yes.
wobbles back and forth. Don't be turning. And the thinner that is, the higher the frequency it is, and you can regrind them. That's what radio amateurs spend a lot of time doing, including myself, taking military surplus crystals that were outside the amateur band and
Yes.
grinding them.
Grind them thinner or changing the shape?
No, grind them thinner. You have to be very careful to grind them evenly on both sides, or if the two faces aren't parallel with each other, they don't oscillate, so you have to be careful.
Oh, wow.
Do a little grinding on one side and the other. So. It was all done, yeah. Grinding, you clean it off good, popped it back together, measured it again, and
Measure it again and see if
took
you
it apart and did it.
Wow. This is all military surplus stuff.
Yeah.
Paper thin, man,
That's insane.
isn't it?
Surprised it doesn't like shatter.
Well, you get too much current, they will.
really?
Yeah.
Too much current?
There are certain
Oh.
certain types of oscillators that were known as rock crushers because they were notorious for causing crystals to shatter. You know, so,
Oh, wow.
so hopefully under normal conditions, the vibration is just a few tenths of a micron back and forth. You know.
So that's enough.
The indented side goes crystal
Yeah.
against the crystal. So it's still locked in on the corners then, huh?
Yep.
Okay. It's just the center of it is able to wiggle just a little bit. There was just like that. No kidding. How long do you think it's going to take for us to recreate this after the apocalypse? Huh?
You're right.
After the apocalypse.
We're toast.
Another 2,000 years?
I remember somebody did a study, you don't realize how much technology that we had to build on it. Somebody said that you take 10 of the smartest guys in the world and they have to combine all of human knowledge, send them to a planet just like the Earth, with all the same resources, but equally distributed the same way they were on the Earth.
Right.
Mm-hmm.
Going down to Brazil.
And not even having to learn how to do it. They already know how to do everything.
Right.
But you go there, okay, well, we need to refine some iron. Okay, well,
Right.
you need to get some fire. Where do you get some fire? Well, you got to get some, where do you get a horse,
You're
So
right.
you take combine, you go
In
to
the warehouses.
it would take them
No.
2,000 years to come up with a V8 engine.
No
That's without
kidding.
even knowing how. That's with knowing how to do it already.
Right.
Knowing every detail of it.
Yep.
It would take 2,000 years to build the infrastructure.
Wow.
No kidding.
Yeah.
To build the infrastructure, I believe it.
you know.
Wow.
So,
I believe it too, 100%.
Right, it's more than just the knowledge. It's,
Yeah.
and it always has been. It's
yeah, you gotta have the resources.
Well,
you
there was
know.
a comedian that was going on about that. It was like if you took a modern man and threw him 2,000 years ago, and you know, it's like, oh man, we have these things we call vehicles. Really, how do those work? I don't know. I can call my family halfway across the world. Really? With what? A phone? How does that work? I don't know.
But and they did it with the smart guy. You think, okay, you take a farmer there, you need a farmer, you need you need all the practical stuff. You need a cowboy, you know, to go and catch the animals out in the wild. So you had all the practical things you do. We wouldn't think about as geeky engineers, but they said, okay, you need someone like a counselor to keep everyone from killing each other. And so it's like all the things you really need as a society to build. You really need a working society before you can even start thinking about building that stuff, you know. So.
That's crazy.
That's right.
I'm glad we live now. I got 2 titanium hips, you know. I'll tell you, I'm super glad I live.
It's a perfect period, right, between now and the AI apocalypse.
That's right. Yeah, that's right.
We get to enjoy it before iRobot becomes a reality.
That's right.
Will Smith has to save us all.
Now that we have a stable oscillator.
Let's slap that robot back to. Okay. Now that we have an oscillator.
I have an oscillator. It's generating a nice, stable, frequency stable signal. Now, you may have several, usually in one of my classes, somebody comes up with things. Isn't a stable oscillator a contradiction in terms? Because it won't oscillate if it's stable, right? The thing that makes an oscillator oscillate is it's unstable. Well, what we have to define is frequency stable.
Right.
It has to be unstable to oscillate, but it has to oscillate in a stable fashion.
Yeah.
The high Q. It's a
The high Q.
consistent.
Yeah. Precision.
Wow.
Consistent oscillator.
So it's precision chaos.
Love it. Now that I understand.
So now we don't have to look too hard at the internal workings. We have an oscillator. We can replace all that stuff with crystal and everything.
Wow. Thank God.
With an oscillator. Well, if this is a real class, I'd make you build one from scratch.
I bet.
So we have an oscillator here. It oscillates at some frequency, and then we want to amplify it.
We're calling that an oscillator.
That's oscillator. So that's generating some signal that resembles it. Yeah, let's be a little more realistic. Out of an RF oscillator, you're probably going to have something that looks maybe like.
Oh, really?
Yeah. So what we have to do is we have to filter out any of the harmonics that we have in it, you know. So because we're driving this transistor into cutoff, and then cutoff rings, and then you can also end up with oddball parasitic oscillations as well. So maybe if we have some time later in the course here, we can build some oscillators to show what they really look like. A true sine wave oscillator is a real tricky thing to build. Matter of fact, the first person ever did it, or people ever do it, were Hewlett and Packard, and the Hewlett and Packard Corporation was started because these guys figured out how to make a sine wave oscillator.
Wow.
So the rest is history. So we start with this wave. Well, I'll be a little more generous. Okay. Okay. Got all these harmonics in here, so then we can run it through a tune circuit. And you can. There are several ways you can build a tuned amplifier. You just have a tank circuit in front of it, and a tank circuit after it. And I'm just showing a block diagram of it. We have our tune circuit here. And out of here, we now have a signal that's stronger and closer resembling a sine wave. That's frequency one. Now, what's really interesting is it doesn't matter how trashy that thing looks like.
Really?
It's going to still be on frequency because it's only the fundamental that you're worried about. Even if you have a bunch of garbage on it, the fundamental frequency, if that's stable, you can always extract that. So that's kind of a neat fundamental principle there. So we can start with a really lame looking signal, and when we filter all that out, this sine wave is going to be exactly the same frequency as the fundamental.
Sure.
Now, we'll talk about it later when we go to FM transmitters, where it's, how we can actually,
And what is this process called? You're calling it,
well, you call it tuned amplifier, it's just amplification. RF amplification. And bring it up to the power level that we need to transmit, so we need we're running high power AM transmitter, typically 50,000 watts, or medium high power transmitter, like 10,000.
Amplifying it?
Amateur transmitter, but legal limit is 1,500. So
Legally.
like your two-way radio stuff, mobile radios, and it's usually around 100, 200 watts there. For the taxi radios, police radios, that's
Sure.
right.
Okay.
Cell phones are usually about a quarter of a watt out. The transmitter itself is a few hundred usually. Cell phone, which is a good thing, otherwise you'd be cooking your brains all the time.
Still.
So, our final stage is let's say our final stage is a tube here, we amplify it up to the point where we can use the tube amplifier. And we talked a little bit about coupling energy off of that was when Kevin was here. Kevin came here for Saturday school, and we talked about the tuning network of the high power transmitters. So.
Mm-hmm.
Anyway, that would be a simplified circuit of a tube amplifier. Stick RF into here, get more RF out here. This tune circuit is tuned at the frequency you want, and we use a magnetic coupler to couple out to our antenna. Now, that's kind of an old way of doing things here. This magnetic coupling is usually not used in modern transmitters. Some of the reason is because you have your plate voltage here, and if that shorts across there, you got your old 10,000 volts there, or whatever you're running at, showing up on your antenna, which is not a safe thing. So,
Not safe.
So most of your transmitters now don't use any magnetic coupling at all. They use what's called a pi network. And well, we are talking about transmitters. I guess we could talk a little bit about that. So we have a tube amplifier here, and this is a choke here. This choke here, all it does is allows the DC, gives us a path of DC through the tube, so the tube will operate, but it's high enough value that it doesn't have any effect on the actual RF. Extremely high compared to the resonant frequencies.
Okay.
And we have what's called a blocking capacitor, plate blocking capacitor, which prevents any DC from going past this point.
Mm.
So all this will transfer is signal. And then we have the real fun part of the circuit. And this is going up to our antenna. And I'm going to turn off one of our heaters here. You guys warmed up enough.
Yeah. Those are variable capacitors, or whatever you call them. Hmm. Do you understand why we're having all these capacitors and inductors there?
Okay,
Okay, go ahead.
so
But those are tubes, right? So that's a tube,
that's two, yeah.
and that one too?
That's a triode, yeah. Doesn't have to be a triode, it can be a multi-ode.
Okay, and the same thing with that one over
Yeah.
there.
No.
All right. Got it. And the one on the right is called a what?
Well, this is just your conventional tank circuit with inductive coupling. And this is a pi network here.
Pi.
Looks like the letter pi.
Oh. Uh-huh.
So this will use everything Kirchhoff's law, right?
Oh, boy. Okay.
So just looking at what's inside this dotted line here,
Uh-huh. Yeah, why?
is that a series or a parallel circuit?
I guess we'll say it's series.
Both.
Well, right, because they're grounded, and then, wait a minute.
Yeah, that would technically count as series, wouldn't it?
Why would that, let's see.
If there's no alternative path for anything to go down other than one or the other.
Ground. And, parallel.
Since these are both grounded, we can just tie those together, right?
Oh.
Okay.
Ah! Okay,
Right? So now, those two capacitors are in series with each other, right?
they are.
But they're
But
parallel,
they're parallel.
they're a parallel conductor, so it's a parallel resonant circuit. So it behaves like any other parallel resonant circuit.
Resonant.
The only difference is we have this part here, we have a voltage divider between there and there.
Right.
And the purpose of that voltage divider is to adjust how much loading we have on the circuit. We want to match the impedance of the two to the impedance of the load here. So what we can do is we can adjust the ratio of that inductance to that capacitance, and if that capacitance is very large and the inductance very small, we're going to have very low voltage drop across it. If we just take this part of it, it looks like a voltage divider, right?
Mm-hmm.
And the greater that capacitance is, the less the voltage drop is across it, because the reactance drops. Right? It's on the bottom.
Hmm.
Okay, so as we increase that capacitance, this reactance is going to go down, the voltage drop is going to go across there, it's going to be reduced, and we're going to have less voltage across our load. And since E squared over R determines the power we're putting out, that's going to reduce the power as we increase that there. Now, one thing we want is we want to have the circuit always resonant at all times. So since these two capacitors are in series with each other, if you change one, you're going to change the resonant frequency. So the resonant frequency is actually the summation of those two capacitors.
Yeah.
So there's going to be some interaction between here. So what we do is we adjust the loading to where we want to be. Last step you always do is we adjust the tuning so this is resonant. Now, Kirchhoff's law. How do we know this thing is resonant looking at the characteristics of the tube? Well, let's put a current meter here. Put an ammeter so we can measure the plate current at all times.
Yeah.
Yeah, amps. So with that, looking at that, how do we know that that's resonant? As we tune through resonance, how do we know we've hit the sweet spot?
The current will, what will happen to the current? Will it peak or will it go down?
It goes almost gone, or the flat lines, right? Basically.
What do you say?
I know you've got the two lines.
Voltage will go down, like you said, so the current goes up.
Let's look at just a simple tank circuit.
Okay.
Well, I got some dark colors that show up on the TV, but
Ha-ha.
not dark ways.
Oh, yeah.
Okay, so here's a tank circuit. The tank circuit is nothing more or less than a parallel resonant circuit.
Yes.
And we'll put a generator across here. And we can let's put an ammeter here just for jollies. And we can do that. Okay.
Uh-huh.
We'll make one variable. Now, there's a node, right?
Oh,
Okay. Now, assuming there's no resistance inside the circle here, what's going to limit the current at resonance?
Nothing.
There's nothing to limit it, okay? So what do we know about any circuit that's at residence? What's the definition of residence?
You said it the other day. It's,
How do you define residence?
think, was it phase? Well, maybe it's not phase, it's,
X of L equals X of C. Reactances equal and opposite and they cancel out. Okay?
right,
It looks like a piece of wire, okay?
yeah,
How much resistance is a piece of wire? Well,
none.
none, okay? So we have nothing to limit the current here, flowing through here, okay? So never be afraid of the infinity. Infinity is a
Right.
perfectly good number, okay? So going into the node, what sign do we define as going into a node? What do you define as positive? Well, if it's going into node, it's positive. It's coming out of node, it's negative.
Right,
So we have, going into this node, we have positive infinity. Coming out of this node, we have minus infinity.
uh-huh,
So how much current can go into here?
none,
Infinity minus infinity is 0, okay? So that's left over, so we have no current going through here. So when this is resonant, we have maximum circulating current here, but minimum current there.
none.
So
That's
yeah,
how
in this case, we'd have none. Now, the only reason we have some is because we aren't totally recovering all that energy because we're pumping it out to an antenna.
Yes.
Okay.
So.
So what we want to do here is after we've done any kind of adjustment on the loading on the antenna, we adjust the tuning to get a minimum on the plate.
Get a minimum.
Minimum.
Uh-huh.
And that's one of the first things you learn when you work with broadcast transmitters. If nothing else, you know how to adjust the plate curve.
Yeah.
They'll prevent you from melting things down.
On your ammeter, it'd be minimum, right, right. I see.
So one of the functions of the Pi network in a Class C amplifier, we finished the sidewave, right? We're in a Class C amplifier, we're only transmitting during very short pulses. Then we have a very strong minus bias on here.
Huh.
So we have a C minus, C is our bias, in a tube amplifier. And we have a very strong, much negative, so this tube is cut off, clearly cut off, so without any input signal, you have no current drawing. And as a matter of fact, this is many times the cutoff voltage, so whatever voltage it takes to turn the tube off, we go 5 or 10 times that. So very, very, very high negative bias on here.
Uh-huh.
So we have to overcome that with a very strong signal here, so now we're only going to get conductivity when this wave overcomes that. Okay?
Okay.
So if you were to just look at the current pulses on here, you would have a current pulse like that. Or if we look at the voltage here, because the currents could be inverse. And we'd have another one here, and maybe another one here, okay? The only time we have
Just
these
the
current
bottoms
pulses, yeah, so we're missing all of that, okay?
We're missing all of what?
Everything below this point.
Oh, right, right. And again, the current pulse is inverse in a
Yeah,
way?
well, the voltage is going to be inverse. Current's going to be the positive voltage. So we can
Oh, I see.
Yeah, you look at current of voltage is going to be equal and opposite. So now we have all these pulses of current, which is not a very good sine wave.
Right.
So we got to fill in the rest, okay? So we need something to fill in the rest here. Okay?
Elves.
So the way we do that is with a tank circuit, a residential tank circuit. So we shock excite it with pulses periodically, and then it fills in all the rest.
Oh, wow.
That's called a Class C amplifier. It's just like a one-lung engine, you know. You got a piston popping everywhere, and the flywheel takes care of the rest.
Wow.
So it's just like a flywheel, fills in the rest of the cycle.
As it powers up and powers down.
Yeah, well, it just oscillates it.
Oscillates.
Yeah.
Yeah. Wow.
Class C amplifier, you can approach 90% efficient with this.
90.
90% as opposed to the Class A amplifier where you max out about 25%.
Wow.
So this is what's used in the final amplifier of 99.9999% of all radio transmitters.
Wow.
Broadcast, I should say broadcast transmitters.
And that's connected, and then the antenna off the bottom.
Yeah, yeah, we could do that here or use a Pi network. Pi network also will
Oh, I
do the
see.
same thing.
Okay.
That's called a Class C amplifier. And, it's the heart of all your high power transmitters.
Wow. And that's not, that's not creating a perfect sine wave, but it is.
It'll be pretty close to it. If you design it right, it's going to be very close to it.
Okay. If
You might add some additional filtering after it, but the
Sure.
whole point of that is to fill in all the rest of
right
it.
there.
Yeah.
Wow. Mm-hmm. Mm-hmm. Wow.
Okay, now talk about something, moving back lower in power here. We mentioned that most fundamental oscillators, or other than, well, even a crystal oscillator, the oscillator itself is going to have several harmonics. Okay? It's not going to be perfect. Now, we know that any harmonics we have are going to be exact multiples of the frequency that we're generating. So we can take advantage of that. If we want to get up to the UHF frequency, or even VHF, very difficult to make a crystal oscillate that such a high frequency.
Mm-hmm.
With a fundamental crystal, it's getting really, really thin, around 30 megahertz. The crystal is going to start getting paper thin, so we can't rely on the crystal oscillating at the Carter frequency we want. So what we do is we start with an oscillator here, which is rich in harmonics, creating something other than a square wave, or other than a sine wave. Let's say something like that.
Huh.
Now, since we have those harmonic content in here, what we could do is we could select the harmonic we want. So let's say we have an amplifier that's tuned to the second harmonic. So let's call this, let's say we want to get 150 megahertz, or even have a broadcast band 100 megahertz. So let's start with 10 megahertz oscillator, and this could be a crystal oscillator maybe. And now, what we can do is we can build another amplifier. Let's tune it to the third harmonic. Okay, so we have just a tuned circuit. Rather than tuned to 10 megahertz, we have it tuned to 30 megahertz. Because we know we've got some 30 megahertz components in that waveform.
Okay.
So then we amplify that, and now we got 30 megahertz here. And then we can maybe multiply it by 3 again. Okay. So then we bring this up here to 90 megahertz. And we have 90 megahertz. Well, they quite right. So what do we need to do? We can start with slightly higher here. Take 100 megahertz divided by 4, which is, let's see, divided by 9. What's 100 divided by 9? It'll be about 11. Well, you can scoot that up to 11 megahertz. So if you look at all these oddball frequencies, if you look at these crystals here, they usually have two markings. One of them is the actual crystal frequency itself. And the other one's the actual transmit frequency, because they can do all sorts of gyrations to get it finally to where it is. It can either be a subharmonic of the frequency you want, or it could be a subharmonic plus an IF frequency. A lot of transmitters actually use super heterodyne techniques to get the frequency up to where you want. Especially nowadays where you have, like cell phones where you have multiple frequencies that are routing. So it's usually a super het type situation there. So you use a combination of both frequency multiplication and mixing to get to where you want to be.
So it's the amplifier that increases
It's
the
tuned,
frequency.
it's tuned, it's tuned amplifier.
Tuned.
Yeah. So it's very easy to get second and third harmonics. Any higher harmonic than that in one stage is a little tricky to get. You can get a fifth harmonic, you could, there might be some fifth harmonic energy in here, so then we could actually go to, 50 megahertz or something in one step, but that's usually 2 or 3 to 1 frequency hop in multiple in each step is about all you want.
Oh, in each step.
In each
But
step.
then you can go again.
Yeah, you can go as many steps as you want. And that's usually what you have to do to get up to microwave frequencies.
Right. Okay. Oh, wow.
Now, since AM broadcasting is kind of where this all started, I'll talk a little bit more about the techniques that are, I should say, nowadays it's a narrow niche of radio, but it was everything at one time. So in AM broadcasting, we know that we have to, first of all, generate a lot of carrier power, and then we have to modulate that somehow. Now, when I built a little modulator here, I was just working with a few milliwatts, and it's called low-level modulation. I could have taken that signal that we had and amplified the daylights out of it, but linear amplifiers finally got them where we want. Very inefficient way of doing that. In all AM, modern AM broadcasting, including shortwave broadcasting, anything running high power, the modulation is done at the final stage. It's called high-level modulation. So we generate the RF at full power, and then we modulate it at full power. So what that tells you that you need an awful lot of audio to do that. So if you have a 50,000 watt AM transmitter and you want to fully modulate it, you have to have 50,000 watts of audio, which is a lot of audio.
Yeah.
So let's talk about how they actually do that. So let's say we have a final amplifier tube, and we've done everything we need to generate the RF, and there's this plate choke. Its purpose was to keep give a DC path for a tube. We need to somehow get the high voltage to the plate here. So we use a choke here, and then we use a decoupling capacitor to prevent the DC from showing up on the antenna. And we have like a pineapple here.
And that's coming from the.
So what we have to do is we have to modulate this plate voltage. Now normally this goes through a big old rectifier, and at KJP we had 25,000 volts on that, so there are lots of power and voltage here, and then we have to somehow modulate that. Well, the traditional way of doing that, you have a transformer here, big iron core transformer, and then you have your DC power supply down here.
Okay.
Which is your nominal plate voltage here. And then you have the primary transformer
Wow.
is driven by push-pull pair of modulator tubes. This one's upside down here, and right here,
More tubes.
right here, this goes for B plus. B plus is your plate voltage. So we have plate voltage for the tubes here, and then we have another transformer here. And then that would be our bias supply, which would be minus C. Now it's not as extreme as the bias we have here in class. This is called a push-pull class B modulator, when the tubes are right at cutoff. So you adjust this bias voltage so the tubes are just barely at cutoff. Unlike class C, where you run it many times by cutoff.
Right.
So right at the verge. So what that allows you to do is this tube amplifies positive half of the cycle, and this tube amplifies negative half of the cycle.
Ooh.
And
Okay.
then we use our driver stage here. This can be a class A amplifier or something here. They got a few transformers involved in here.
Yeah.
And the power of this has to be about equal to what the power is we're putting out of here, whereas the driver stages can be much lesser. So that's your basic, very rudimentary system. System of
What would you
AM
call it?
modulation.
This is.
It's called high-level modulation, also called plate modulation, because we're modulating the voltage on the plate. Now, we mentioned that Class C is nice because it allows you to run very efficient. If you want to modulate it, it must be Class C. It cannot be linear, because if it's linear, all you end up doing is adding one wave to the other, which is not modulation. It has to be a multiplication process. So this must be a Class C, or it could be another highly nonlinear, but there are other very inefficient nonlinear amplifiers, but we want a Class C amplifier that's both highly efficient and does what we want to do.
You're saying if it's not, then it adds to
It adds, yeah.
It adds
So
to
we
the
don't want to
frequency
add,
or amplitude.
just adding the audio to the carrier doesn't do anything. All it does is shifts the DC level carrier. Space doesn't recognize the DC potential, right? So you have to actually increase the RF and decrease in accordance with that. So it must be a multiplying property.
Okay.
So here's your rudimentary high-level AM transmitter, which is 100 years old. Not these actual markers, but basic design is 100 years old. Can't get much more
And what's
low-tech than
between
this.
these amplifiers? You said it's a steel.
Oh, that's steel core transformer. That's your modulation transformer. The two bars there means it's an iron core. This.
Did you learn about transformers? Did you really go into transformers?
Well, you just pretty much use zero core transformers. You just have two coils next to each other. So when you go to lower frequency, you have to
Yeah.
lamination to concentrate the field. Now, we mentioned that having a high Q is always nice. Well, most of the time it's nice because it makes a very clean signal. It gets rid of all the harmonics that we don't want,
Right.
and the efficiency can be very high. But you can go too far. What do we have to do? What do we have to accommodate when we're broadcasting AM? Because we're not just transmitting a carrier anymore. We've got information, right?
Right. But there are, well, the carrier can create its own.
So let's put this line here, and this will be called our frequency line. Okay, F sub 0
Okay.
is our carrier frequency, and this is amplitude.
Okay.
And so if we're modulating an AM signal, we have a, let's say, a 1 megahertz carrier, and we're modulating it with 1,000 hertz audio. What do we have in addition to our carrier here?
have that, mirror image, or what was that called?
Sidebands.
Sideband.
We have LSB. Upper sideband. And how far are those sidebands away from the carrier?
I thought it was addition of,
Yeah, it's the audio frequency.
That's the audio.
Yeah, the audio frequency above or below and below the carrier. So if we're putting 10,000 hertz in here, we're going to have plus or minus 10,000. So we have to accommodate the entire.
right,
Now, standard AM broadcast in the U.S. rolls off around 7,500. Actually overlaps adjacent stations, but that's why you don't have adjacent stations in the same market. But we, if we really do it with the latest technology, we usually have plus or minus 7,500 there, so we have 15 kilohertz occupied bandwidth. Now that's a maximum. Of course, we're going to have all this other stuff in between here because we're never sending just a single tone when it's transmitted. You got
right,
the voice or whatever else.
oh, so there's sidebands all across it,
Yeah.
makes sense. And that's the, okay. And you're adding the amplitude of the,
Yeah, if you take any with a single pair, fully modulated, you take a single pair of sidebands, you modulate the transmitter as much as you can. Remember, when I was showing the waveform there, I could make them overlap where they actually crosses over to past zero. Well, you can't get any more than past zero because that's no power. So if you have full modulation where it's just touching zero at the lower part, and twice the amplitude at high power, that's called 100% modulation. And in that case, you have half your total powers in the sidebands.
uh-huh. Yeah, okay.
So if we add the power in the sidebands to the carrier, we know obviously you're going to have more power when you're modulating than when you aren't. Okay? If you look at your antenna current or your modulation, when the DJ finally shuts up, the antenna current drops, and when it starts yakking again, you know the carrier's the same power. Okay, so we want to, let's talk a little bit about FM. It's most of your VHF communications point-to-point are FM, at least at VHF. You know, for long distance, we usually use single sideband or CW or some other means. But for the most commercial stuff that we're using, like two-way radios and cell phones and everything else, it's usually FM of some sort. So,
Oh, it is FM.
yeah, it might be frequency hopping, but it's still FM. You know, some use a combination of both AM and what's called quadrature modulation. We'll talk about that later on. But FM broadcasting, of course, is FM, and all your police and fire radios and public service stuff is all FM. And so FM has some advantages and some disadvantages, and we'll talk about those. So FM was originally developed to be less subject to static than AM. And the reason is, in the receiver, what you can do is you can take the signal and you can lop off any amplitude variations. So you basically lop it all off there. However, if you lop off on an AM signal, lop off all the amplitude variations, you're left with nothing. So how can we do that and keep information? Well, what we do here is on AM, we're taking the audio and we're applying it to a transmitter and changing the transmitter power in accordance with the FM, in accordance with the audio.
Right.
In FM, the power stays the same at all times. We aren't changing the amplitude at all. What we're doing is shifting the frequency back and forth in accordance with the audio. So if we had a low frequency audio like this and a high frequency carrier, it would or RF would do something like this and stretch out and approach the compressed there. So the frequency frequency is going to be shifting in and out there
Oh,
over a narrow range in accordance with the audio here. So as the audio level goes up, the frequency is going to shift one direction.
the audio tone, like the frequency of the
Well,
audio.
it's actually both, but actually the amplitude. So the
Oh,
signal,
the amplitude.
the amplitude is going to follow that. So because it's a function, the amount of what we call the deviation is a function of frequency and the amplitude. So we have some really complicated looking
Wow.
sidebands when it's all done with. So,
I bet. So that audio is just volume of the audio.
at any particular point. So with a single tone, it's going to look like this. So you have a single tone. With multiple audios, we're going to have a bunch of multiple tones together.
Right.
And the frequency is going to change in accordance with the instantaneous amplitude of those tones.
Okay.
Again, the total power is never going to change. This amplitude is going to stay absolutely rock solid.
Right.
So the
Just
FM
the
transmitter,
frequency is
FM, one of the advantages of this is since you don't have to keep any of the amplitude information, a Class C amplifier, you can use Class C amplifiers all the way through. Very efficient, since you aren't trying to maintain any amplitude information at all. There's no valid information in amplitude.
Okay.
In the receiver, what we can do is we can amplify the daylights out of that thing.
Huh.
And just cut a slice through the middle here.
Right.
And let's say there's a bunch of noise riding on top of that signal there.
Yeah.
We never see it. All we're looking at is the crossover points here
Wow.
in the middle here, and which is never going to change. That's going to be depending on the frequency. So we're going to lose any noise information on here. So all we're going to see is the frequency information at any point in time. So
How do
And-
they achieve that?
with that,
How do they achieve that, though?
with that, okay.
And again, that information is telling you the volume of the audio and the frequency
yeah.
of the audio? Wow, okay,
Yeah.
let's hear it. That's, yeah.
So the first thing they need in order to do that is to have a voltage-tuned oscillator. So we start with an oscillator. And it can't be crystal control, well, it can slightly, well, but normally not. So, well, for pure FM, now we'll talk about phase modulation, but direct FM, we'll call this direct FM, the simplest way. You usually don't have a crystal controlled oscillator because you have to move that. Crystal controlled oscillator is rigid solid, doesn't want to move, okay? So you have to change the frequency of that.
Oh,
So we use a device, and they're, back in the olden days, before varactor diodes were used, they used what's called a saturable reactor. Saturable reactor is a transformer that's actually allowed to saturate, which means is if you put a DC current through it, it'll reach a point where it starts losing its permeability. So you're changing the permeability of an inductor by putting a DC voltage through it. When you change the permeability of the inductor, the inductance changes.
uh-huh.
And then if you use that inductor in part of a resonant circuit, the resonant frequency is going to change as you change.
Wow.
Well, we no longer use saturable reactors for like that. We'll use what's called a varactor diode. And any diode will varact to a certain degree. The symbol for varactor diode is this.
Huh.
And what it is, it's just a diode, semiconductor diode, but it's specifically designed so that as you change the voltage on it, the internal capacitance of the diode changes. There's what's called junction capacitance between the P and the N junction in any diode. And the actual size of the junction changes depending on the voltage, so it actually looks like you're moving the plates farther and
Wow.
there. So it's what we call a varactor diode or a voltage variable capacitor.
Capacitor.
Yeah. So you're looking at the capacitor's value on here. So we can build this as part of a tuned circuit. And this would be our oscillator circuit here. And so then we apply our audio to this, which is our low frequency audio signal. We apply it to that. That audio changes the value of the capacitance in accordance with the amplitude of the audio at any point in time. And as the capacitance changes, frequency shifts. So we slightly change the frequency of this. And voila. Usually uses very small changes of amplitude. Now, what they call DCFM, where direct carrier frequency modulation, which is used in a lot of modern FM broadcasters. This is actually done at your final carrier frequency. Traditionally, on your two-way radios, that sort of thing, and older FM transmitters, use what's called indirect FM, where you start with a crystal-controlled oscillator, because it's very stable, and then use a phase modulator after that. So we start with a fixed frequency, and then we use pretty much the same technology here. Use a varactor diode or something like that. It's just part of a tuned circuit, not an oscillator, but just as a resonant circuit here. So, because of good old Eli the Iceman, when this is at resonance, there's no net phase shift. As we change this value of capacitance, the phase can be shifted up or down. So we're starting with a fixed frequency, but adjusting the phase. So it's called phase modulation. Now, what makes phase modulation different is that the amount of perceived frequency shift goes up as the frequency of modulation increases. So in other words, higher audio frequencies are going to cause more of a deviation of frequency than lower frequencies. So you have an automatic thing called preemphasis, which is built into it. Built into that. So
properly measure that.
Yeah.
Okay.
And so what you have to do is in the receiver, you have to use de-emphasis to undo that. so that you have equal deviation.
Is it exponential in a way? Yeah.
You want equal deviation across the entire audio spectrum that you want. So
right.
Otherwise, it's going to sound very tinny. Your high frequencies are going to be amplified more than low frequencies. So, so phase modulation, I use most of your amateur radio, handhelds, police radios, any of the lower affordable radios. Now, on either frequency or phase modulation, if we use very, very small increments, and for example, if we want to go to, we can get very small shifts of frequency with a crystal controlled oscillator.
Oh.
But it's very, very small, so it's not going to do us much good, okay? Because it's going to be equivalent to very, very low modulation. We're not going to hear much, okay? But what we can do is if we start with our oscillator at very low frequency, and we talked about all the multiplication, you can multiply any carrier frequency as much as you want, by as many steps as you want. You start with a lower carrier frequency here, and then every time you multiply the frequency itself, the actual deviation multiplies the same amount. So if we have just a few hertz of deviation on that, as you multiply it, the amount of frequency swing is going to change by the same degree that we change the frequency itself. So let's say we have a 36-to-1 frequency multiplication scheme. That means our deviation, whatever we started by varying, is also going to be varied by 36-to-1. So we have a few new terms that we want to talk about.
Nice.
Unlike AM, where we have percentage of modulation, which is how much change we have in our amplitude. On FM, we have what's called the modulation index and the deviation ratio. So, with a single tone, it gets really complicated when you FM sidebands are incredibly complicated. There's a whole branch of mathematics that kind of defines it called Bessel functions, and I don't know if there's anything in the text that off there. If there are any, let me know, and we'll talk over them. I don't think it's on the FCC test, but it's a way of calibrating your test equipment. Anyway, we have a carrier frequency here, and again, the total power is always going to be the same. Unlike AM, where you change, or FM, all you're doing is redistributing the power. As you move this thing across the spectrum, we're taking that given amount of power and moving it at different locations. So,
right.
The amount of deviation we have from the carrier is called the deviation. Obviously, pretty self-explanatory there. So, a typical communications radio, we might have 5 kilohertz deviation. And that's the maximum deviation you have. Now, what's really one of the figures they give you is what's called the deviation ratio, which is the actual amount of deviation for a given frequency. And as we mentioned in FM, or phase modulation, the amount of deviation changes depending on the frequency,
Right.
as well as the amplitude. But for a single frequency, the louder it is, okay, the more deviation you're going to have. So very quiet signal is going to be very small deviation.
Okay.
Very loud is going to be very wide deviation. So we can, on the first order, we can assume that the deviation and thus the total occupied bandwidth is going to be proportional to the loudness of the modulating signal.
Okay.
But it's also a function of the frequency as well. So we have the first order for the loudness, but then we have the frequency, which gives us all these really oddball sidebands. Now, if you remember the sideband distribution for AM, with a single modulating tone, we have just one pair of sidebands.
Mm-hmm.
And those sidebands are separated from the carrier by the modulating frequency.
Right.
On FM, you have an infinite number of sidebands for any given tone, and the separation between those is equal to modulating frequency. So actually, if you have a 5 kilohertz tone on here, we're going to have an infinite number of 5 kilohertz separated sidebands. Now, because there's an infinite number, how do we deal with it? We call them significant sidebands.
Okay.
So,
and then you're reading from other stations too.
well, yeah, I mean, so
They figured that out, obviously.
Yeah, so-
Okay.
So what we have to do is we have to talk about the significant sidebands, which are basically the sidebands which would fall within the same bandwidth as if it were an AM signal.
Okay.
But
And again, 5 kilohertz.
that would just be if you're modulating with a 15 kilohertz tone, we have all these 15,
Right.
an infinite number of them.
Going at, yeah. Wow.
So
Frequency.
but theoretically, every FM signal is infinitely wide. Now, theoretically, but,
Okay.
but there's other things that limit it. So.
Right.
There's a lot of infinity in
Yeah.
radio.
Yeah.
Math like this.
Yeah.
So
Wow.
now the techniques for amplifying FM is very simple. It's Class C amplifier all the way, and you do all the modulation at very low power and very low frequencies. So you just do it all thing right at a few milliwatts and amplify the daylights out of it later. And if you need to get more deviation, you just run through more multipliers. You know?
So if FM was developed to be, cleaner sounding,
Yeah, well, it's mainly designed for noise immunity more than that.
yeah.
Now
Why do they still run both?
there's a couple other factors in there. At VHF, the last holdout of AM on VHF frequencies is aircraft radio. Now, one of the things that makes FM so clean is a thing called the capture effect, which means if you have two stations on the same frequency, the stronger one is always going to totally override the weaker one.
Oh.
Which is a very good thing if you're trying to get rid of interference, This is why it's great for mobile radio. That's the last thing you want in an aircraft radio, where everybody has to hear everybody else.
Right. Ooh.
If you're running your aircraft VHF and you're the strongest one, you're the only one anybody's going to hear.
Right.
So that will never go to FM because, capture effect, very good, very bad. So that's
Screaming into your radio and nobody can hear you.
well, they'll hear you, but nobody else.
Wow.
So whatever's strongest, so that's what makes so interference free on mobile. But
I see.
another thing is the occupied bandwidth of FM is a lot more. For a typical FM channel, broadcast is 200 kilohertz, where the AM is 15. So 10 times the bandwidth for. So you don't have that bandwidth available. Now when you get to shortwave radio, what really happens if you try doing wide bandwidth there, first of all, you don't have that much spectrum. The lower frequency you go, the less space you have to do that kind of stuff. But if you could, you have another phenomenon called selective fading, where different parts of the signal have different propagation paths. So when you have all your signal compressed together there, your upper sideband or lower sideband pretty much take the same propagation path. And you start widening that farther out. You start out with one radio transmitter to have signals come out completely different places depending on where the frequency is you're operating.
Wow.
So selective fading became a real problem when shortwave radio broadcasting first came in.
Really?
That's one of the reasons single sideband was invented to compensate for, was the upper lower sideband dispersion. It's just like a prism. The ionosphere is just like a prism.
Right.
The frequencies are bent fast and low. So you transmit a signal out, and half your signal goes to, so it's like New York, and half goes to Hawaii. So not a good
Really?
thing. So no, it wasn't quite that extreme.
I mean, but, yeah.
Hundreds of miles of difference between the landing point between upper and lower sideband. So FM is generally considered a wideband mode, whereas AM is narrow band. And variations of AM single sideband is 9 or so. But for point-to-point communications, where you work with relatively strong signals, it's really good. It gets rid of all the static. We can just lop it right off and be done with it. So, how do we detect FM?
FM receiver.
Now, we mentioned that just about every receiver we have nowadays is a super heterodyne of some form. So what's the IF frequency of a typical AM radio, AM table radio? 455. Kilohertz. Now, how about car radios?
Car radio?
Yeah.
101.
No. 262.
96.9.
262.
Okay.
For FM broadcasting is 10.7 megahertz. We use 10.7 megahertz IF, which gives us wider bandwidth, which is what we need for FM. Now, what other advantage does having a high IF do? What's the pros and cons of your using high versus the low IF frequency?
Transmission through the atmosphere and whether it's going to...
No.
Nope.
Really has nothing to do with that.
Okay. What's the benefit? How much information you can
No.
carry on it?
What's an image frequency?
Image frequency is the...
What's that?
Modular.
It's your mixer, right?
mixer. Yeah.
And what do we put into our mixer? What's this? It's our local oscillator frequency. Okay,
Okay. Local oscillator, yeah.
here's our incoming signal from our antenna.
Okay.
Now, if we have an IF frequency of 455, where do we want to tune this if we want to receive a 1 megahertz signal?
1 megahertz.
Yeah.
To 454.
No. That's 455 kilohertz.
Oh. And we want to receive a...
And we want to receive 1 megahertz.
Oh. Right. Well, we just...
Be pretty low, right?
545?
It would be 1455.
1455.
Okay.
Okay.
Okay, the difference between those is that, right?
The difference between that. Okay, I knew it was...
Okay, but what else will this respond to?
I thought it was multiplying, not adding.
455, these are added, frequencies are added.
Oh.
What else will we respond to? A... 2455 or 4?
It'll be 1910. It is twice the IF frequency away from your desired frequency.
Twice?
Yeah, so if you take 1910 minus 1455 is what? 455.
Oh,
This is your image frequency, okay?
image, okay.
You don't like
Right.
that, okay?
Right, okay.
So the higher your IF frequency, the farther your image frequency is away from your desired frequency.
Oh, yes.
Remember
Yeah, okay. Thanks for the reminder.
that? So,
Uh-huh.
we usually don't have a problem with image frequencies on FM. 10.7, any image frequency is going to be totally out of the FM band. I mean,
Right.
10.7, if you want 100 megahertz, the other one's going to be like 140 something, and there might be something there, but usually it's far enough away, it's not too hard
Okay.
to separate it out ahead of, before the mixer. So there's a moderate amount of selectivity here before the mixer, and it's no longer a problem. So we take our FM signal, we take our local oscillator, which is now going to be whatever it is, 100 and something. No, so it's somewhere in the FM band, FM between 88 and 108. So. Okay, we'll convert everything to 10.7 megahertz. And now we have a signal here, which is an FM signal. It's still FM when we get it. There's no AM's lopped off of it.
Mm-hmm.
So then what we can do is amplify the daylights out. Remember what happened when we took an amplifier, you drove it too hard, you take the sine wave with the op amp? What happens when you run an input signal? As you keep increasing input signal.
What did you do? It started to was it overlapping? No, what was it doing?
With a single signal.
With a single signal, it got cut off at the top.
Yeah, cut off, it just flattened out, okay?
Yeah.
Well, you do that on purpose here, okay? You take the IF amplifier, just run it till it flattens out, okay? It's not gonna see anything happening above the cutoff points, okay?
Mm-hmm.
So that's all gonna be just lopped right off, which means any noise of the amplitude is gone. So all we're left is a pure FM signal. And that's called a limiter stage, or stages. And all we have to do when we're done here is detect the frequency shift.
Okay.
So how do we do that? Well, it's called, simplest way is called slope detection, and it's variously known as slop detection because it's a sloppy way of doing it, but it does work, okay? Here we have a tuned circuit. It's slope detection, but it's what we call slop detection. Okay, so we have a tuned circuit here, okay?
Okay.
That's a characteristic tuned circuit. As you're in dead center, that's where you have maximum amplitude. If you're off down here, you have minimum amplitude, okay? You have minimum amplitude either side, okay?
Mm-hmm.
So we tune this tuned circuit so that we're somewhere tuned around here, okay?
Interesting, okay.
So as the frequency goes higher coming in, it's going to move higher on the slope, and move down, it's going to be less on the slope. And so what we do is we simply take the voltage at any time and we amplify that, okay? Very simple to do. All you have to do is have an audio amplifier with an off-tuned tuned circuit in there, okay?
Huh.
And that's why it's called slop detection, is because this is not very linear at this point, okay?
It's not.
It's not. It's still a part of a bell curve, okay?
Right. It's okay.
Now, the next revision above that is a double tuned tag circuit, where you have two tuned circuits, one slightly above and one slightly below there. And your resting carriers in between here someplace, right? If it moves higher in frequency, this one starts conducting. If it moves lower in frequency, this one starts conducting. And the non-linearities here tend to cancel out a little bit.
Okay.
So you basically have two tuned circuits, one slightly above, one slightly below. And one's more sensitive to the upward shift and one's more sensitive to lower shift, okay?
And so one will overpower the other in terms of...
Yeah, in terms of voltage, yeah.
Ah.
So it's double slop detuned, double slop tuning.
And you can do that several times throughout that curve?
No, you just use two tuned circuits.
Okay. Wow. That would be maybe more accurate.
Well, it's less distortion than a single tune because the nonlinearity, because we're working on a bell curve, not that straight line, it's gonna give you a little better faithful reproduction.
Ah. My brain. Okay.
So let's see, discriminator. So
Again, the circle with the X is our modulator.
that's a mixer,
Mixer, that's what we're calling
which is a modulator or a demodulator. All it does is gives you a product of the amplitude of two signals, but that converts into a sum in terms of frequency.
it. Aha. You're right.
Okay.
And your local oscillator, how did we make that again? Was that something that you could tune, right? That was something that you were going to...
Yeah, well, all we have to do is we have to have some component in there which changes its reactance depending on the DC voltage we put into it. So we use a varactor diode or a saturable reactor.
Okay, right.
Now we're using the old school way. Now there's newer stuff of doing, newer ways of doing it, like phase lock loops and all that. So we'll talk about phase lock loop a little bit. I think there is some stuff on the test.
This, like for instance, this book you had here, if you said there was an anniversary one,
Yeah.
go a lot more into detail.
They're actually pretty much identical.
As that?
No, this is commercial. That's amateur.
But there's a lot of principles.
Like yeah,
I probably will get into later.
let me see.
This book, probably have to end up getting it. And it went through electronics as well, didn't it?
Oh yeah.
I mean, heavy, I remember.
Okay, let's see if I find a Foster-Seeley discriminator in here.
There's some great YouTube channels as well on electronics. Things that I just feel like I need to hear it several times. It's not like when I was 21. You know? Mhm. Hmm. Oh, you ended up getting that back together, huh?
And it still works.
Sweet.
I actually put together right.
I guess those two brass plates
Let's see.
are sending, yeah.
Now, it used to be on the, I don't see it on the current FCC test, but they used to say, they'll tell you how do you tell the difference between a ratio detector and a Foster-Seeley discriminator. And I can't remember now, so I have to look it up. Working so much with phase lock loops lately.
On my own property, so.
Yep. Mhm.
Found it?
I-
So, are you an electrician? Are you an electrician?
I used to be. Yeah, so I was a tradesman for a long time. I did carpentry and electrical. And then
How long did it take to become an electrician?
4 years.
4 years?
Yep. Then you're journey cop. You become journeyman status, yeah. So you gotta take a test with the state.
After 4 years?
And it depends on
They
which
won't
state
let you
you're in
take the
too.
test before 4 years?
Nope. And Alaska's actually weird because Alaska, like some states, it's a certain amount of hours. And so if you work a ton of overtime, then you can get there faster, yeah. So, because you'll work 4 years worth of hours. Alaska, you have to have 8,000 hours, 4 years, and all your schooling done before they'll even entertain you taking the test. So, back in Kansas, where I'm originally from, it's only 2 years. But the license is not a federal license, it's a state license. So Alaska's license, because the requirements are so high, reciprocates to like 38 different states. So I could go work in other states with a journeyman's license from Alaska, and then go to those that would be recognized. Kansas, because it's only 2 years, nowhere else recognized. you drive an hour. I grew up in southeastern Kansas.
Okay.
And so I was 45 minutes from the Oklahoma border.
Yeah.
We used to go down to Oklahoma all the time.
And then
But if
you
I'd
can't do
have
it.
gone across the border, yeah,
You can't
your license is
officially do
not
it
done.
there.
Yeah.
Wow.
Yeah. So they don't,
Do a lot of people finish their schooling pretty early on and then just work hours?
basically, yeah, if you can. Yeah. Some programs will let you. There's 2 programs that are non-union in Alaska. ABC is by far the worst one.
Really?
Yeah, they suck.
Okay. What's
Avtech,
the other one? Adtech?
Avtech is the
So
other
you
one.
have to pay for these programs?
Either you do or your employer does.
Adtech.
But typically you have to be employed with the electrical company, and they'll get you in the program, whichever one they use.
And again, that's 4 years still. They have
Yeah.
to go through this.
Yep. But Avtech is much more user friendly. It's they'll let you fast track through things if you want to. ABC realizes that as soon as you get out of school, they stop giving money, and so they will intentionally slow your schooling down so that they can keep getting monthly payments from your
So
employer.
it's
So
Adtech or you go to union? Is that what
basically,
you're doing?
yeah, that's what I would do.
What's
Yeah.
the-
And
You
then
do one of those 2?
yeah,
Adtech.
if you wanted to become an electrician, yeah.
What's the disadvantage of going to union, let's say?
The disadvantage of going union is you don't get any control over your own career until you journey out. So 4 years that you're an apprentice, you go where they tell you to, you work for who they tell you to, even if you don't like the guy.
Is it kind of like it's
Yeah, and they will intentionally move you around, which is good because then you'll learn from different
experience?
journeymen.
Oh, okay.
But at the same time, if you really like your boss, they're going to force you to stop working for them in like, 6 months or so.
So, it's not recognized as being sort of a bridge circuit. Remember bridge circuits, we had nulls that happen at certain things. So with a signal coming in here at your carrier frequency, these 2 diodes are going to conduct exactly the same. They are.
Okay.
So if we shift the frequency higher or lower because we don't delay the ice span, one of these sides is going to conduct more than the other. So the bridge is going to become unbalanced, and now what we have is we now have a DC voltage which we can now amplify. So this is very linear. So the amount of DC voltage we get is exactly equal to or proportional to the change in frequency.
Ooh.
So that's pretty cool. Now, back in the old days, you say, okay, if the diodes are facing the same way as a Foster-Sealy discriminator. If they're facing the opposite way, it's a ratio detector.
Huh.
I don't even see that on the test anymore. So
Wow.
I won't make you better. But anyway, if you see something look like that, that's a discriminator, and it would be used to basically converts FM to AM. So it's basically unbalancing a bridge circuit. So when everything's tuned correctly, we have this lag here is equal to this lead.
Ooh.
So, and
That capacitor is equal, that's an inductor down here.
and that's an inductor.
You call that a lead?
Yeah,
Okay. Wow.
so somebody figured that out. Well, not somebody. Foster and Sealy figured it out.
Foster and Sealy, okay. Did they start a company?
Well, they had patents coming out their ears, you know.
Wow. That's all you
Nobody
need.
made the money on the patent themselves. They made the money on licensing the patent.
Yeah, oh, right.
The biggest patent troll on the planet was, well, Edison was pretty
GE,
bad,
Edison,
but
was he?
David Sarnoff from RCA,
Sarnoff, wow.
yeah, he was a real jerk.
Have a lot of those worn out, gone past their period, patent period?
Well, they were true patent trolls before the term was ever invented.
They were, huh?
They,
They wouldn't just license it out, they wanted maximum.
yeah. Well, you know why Hollywood ended up in California, don't you?
No.
Thomas Edison was a patent troll. He wanted to get a patent on the very concept of movies, not the individual things. He wanted to actually patent the whole. The only way he could get them not paying royalties and move clear across the country, and he couldn't have his goon squad.
Really?
Harassment, yeah.
Wow.
If it worked for Thomas Edison, the movie industry would have all still been in New York.
Wow.
But he forced them because he was such a
go to the
jerk.
Wild West.
Yeah.
No kidding.
And wow.
So that's why it's Hollywood, strictly to get away from Thomas Edison.
So now these patents, their time has worn out? And
Well, they keep getting renewed in different variations, you know, so the original ones.
so they're still trolling going, or they've opened up a little bit, it sounds like. Okay.
Well, I know that they've also limited what you can patent these days.
Yeah,
too.
yeah.
They have.
So,
There's certain things that are just common use technologies. And
but
whatnot.
these patent trolls, they rather than having a specific patent, you know, they just have the broad brush stroke. You know.
Right.
Bill Gates, of course, is the most famous for that,
Is he?
but he wasn't the first by far. And
Wow.
Helicopters radio, you know, I have a bunch of Helicopters radios here, but you look at them and all the patents, you know, the tubes there, you know, every type of tube has its own patent there, and they Helicopter. It was basically RCA pretty much owned radio as far as, you know, that's David Sarnoff. So
Wow. Not anymore. It's
David Sarnoff's been dead for 100 years.
right. Oh yeah.
Well, RCA is pretty much no longer around.
Right.
So yeah, most of those original patents are going out. Obviously, with somebody's using vacuum tubes, there aren't any patents.
Yeah, as soon as technology advances, certain ones just become obsolete.
Wow.
So anyway, now that we have a FM signal, which is only dependent on the frequency, we can do the same thing we would with any audio. It's now, after the Foster-Sealy discriminator, it is now in the audio domain, so that we just use audio amplifiers to get it where we want it to be.
Oh, it is in the audio domain.
Yeah.
It lowers the frequency.
Yeah. Because the frequency deviation is at an audio frequency. So we're only looking at the deviation of
Ah, yes. Wow.
So
Deviation.
give it a very, very crude analogy.
Deviation, yes.
This is AM, and this is FM.
Right.
Yeah.
Yeah, that's a very good analogy, actually. Uh-huh. Okay.
So if FM is lopping off the majority of the frequency,
Not the frequency, majority of the
majority
amplitude.
of the amplitude,
Yeah.
could you, overlap those portions to kind of tighten things up in the, I don't know how that would.
No, it's, yeah, you're simply not responding to the receiver, and the lopping off is in your receiver, not the transmitter.
Oh, okay, gotcha.
But then you are responding to many different frequencies, whether it's for volume or
Yeah.
frequency
Yeah.
of the audio.
Yeah, but that's all at audio frequencies.
Oh,
Our frequency is 100 megahertz, whatever.
Right.
Eliminated, so.
Okay. Okay.
So that's where you get the multiple sidebands, and that, again, if
Right.
you look at Bessel functions there. You mentioned Bessel functions in the,
And again, what is that circuit that discriminates and picks?
well, it's called a discriminator.
It's called a discriminator.
Discriminator, yep.
That's why I use that word,
Yeah.
discriminator.
Foster-Sealy is one type of it. There's other ways of it now. A lot of modern stuff is using phase lock loops now. I don't talk about the phase lock loops. It's really going to be using a lot. Everything using it. Okay. Back in the early days of multi-frequency radios, for police radios or whatever, where you need to hop frequencies around, you just have to stack some crystals. That's why I have so many surplus crystals. Got a lot of radios had piles of them. The 23-channel CB radios used to have 23 channel crystals in them.
Really?
Yeah. And so it got to be pretty bulky and expensive to use for frequencies, And so people were looking at ways of how can we get rid of some or a lot of the crystals. And a couple ways doing it. We know we can multiply and we can add, right? So we can take some crystals here and use certain multiplication and adding, and by doing that we can eliminate some of them by using just a few of them.
Yeah.
By different combinations. But even that ended up with bulky, so we'll have some mechanical switching and all that sort of thing. So eventually it was a gradual elimination of lots of crystals. Well, what if we do if we only had one crystal and we made that a reference point and everything else was locked to that?
Right.
And thus we came up with the phase lock loop, which is absolutely a pretty amazing device here. And it's used in everything nowadays. All your cell phones are based in phase lock loop. This function generator here is that.
Is it?
It's called direct digital synthesis.
Okay. Is there a crystal in there?
There's one.
There is one.
There is one. Yeah.
Cell phones have a crystal in it?
Yeah. Oh, yeah. Every cell phone has got a crystal somewhere.
Wow.
So, okay. So
Blown away, man.
So we have a oscillator, rock solid oscillator, and I'll draw a little crystal here just so we can remember that's crystal. Okay.
That oscillator is a crystal.
That oscillator is a crystal oscillator.
Okay.
And it gives us a reference frequency. Now, one thing we can do, if we can take an oddball waveform, and by using filtering, we can get a sine wave out of it. We can do the backwards. We can take a sine wave and make a square wave out of it. And the simplest way of doing that is what's called a comparator, which is basically an op amp with some feedback. And no, actually, without any feedback. Actually, we take an high gain op amp with no feedback. When voltage gets across a certain threshold, let's put a reference voltage here on our negative side, so we could use a voltage divider here. So we have a voltage divider there that sets us as some reference. So, just for jollies, let's use 5 volt TTL circuitry, and let's call that 2.5 volts. Mm-hmm. And we put a sine wave there. Anytime this sine wave gets more than that voltage, it goes low, goes to 0 volts, and every time it goes below that, it goes to high. So 5 volts, whatever.
Yeah.
0 to 5 volts.
There's your square.
So it's called a one bit A to D converter.
It is.
Yeah, 1 bit analog to digital.
On off.
So anyway, so we run our sine wave through there, and now we got a square wave, which is exactly equal to the sine wave frequency. And we can arbitrarily pick that. It can be any frequency you want, but we want to pick something that's going to be convenient to play around with later. So let's, just for jollies, let's call it 1 megahertz.
Okay.
Now, we have a signal that we want to generate. And let's say we want to generate a 100 kilohertz signal. We have a 1 megahertz crystal here. We have a free running oscillator. It's not really free running, it's voltage controlled, okay? We have an oscillator with a varactor diode, which changes frequency depending on the DC voltage. Now, what we can do here is, well, let's start with that same frequency we want. So we have a free running oscillator here. And it's free running, but it's voltage controlled. Now, why would you want that? Because we can try and control our voltage here and get direct FM off of that. Remember, it's very difficult to frequency modulate a crystal oscillator.
Right.
Right? It wants to stay right where it's at.
Right.
This is not as picky. It's a free running oscillator that's determined simply by its tank circuit, and then if we can change the value of one of those components, we can change the frequency. So now we have a reference here. We have our voltage control oscillator where we also go into a square or upper, okay?
Okay.
We take both those signals and we put it into an AND gate. An AND gate is simply a device and we got two high signals that are high, it goes high.
Okay.
If both these are high, this will be high. Both of them are low, this will be low. If one's high and one's low, it's still low, okay? So what this will do is only give you a pulse out when these are actually overlapping.
Okay.
Okay? So we have this, if we look at the output, if one of these drifts from the other, the width of that cycle is going to change, right?
Yeah.
Okay?
Oh,
The
right.
width, the duty cycle, that's proportional to how close they are in frequency.
Right.
So if
When
one
they're matching, and
Yeah,
when they're
yeah.
not matching.
Yeah, well, actually, the perfect match is when they're 50% duty cycle.
Ooh, really?
50%. Yeah.
Okay.
So one drifts higher. Now, what we do is we now take a circuit which averages those. It's called an integrator.
Okay.
That's mathematical integration, and all it is a low pass filter. So we take a filter. If we put a square wave into that,
That's right.
we're going to get a DC voltage out of here, which is proportional to the duty cycle of that. If it's 50%, this voltage is going to be half what the peak voltage is.
Right.
This is let's say this 5 volts here, and that's 0 volts here. At 50% duty cycle, this is going to be 2.5 volts. The wider the duty cycle, the higher the voltage is. Okay. We take that DC voltage, and guess what we do with that? We use that to control the oscillator frequency.
Okay.
So if this tends to want to drift higher in frequency, its duty cycle is going to decrease. It's going to decrease the voltage in here, and it's going to adjust the oscillator down in frequency.
Back towards the quartz crystal.
This is reference. This never changes.
Reference,
This is your reference. All it does is compare the frequency here to the reference.
It's comparing.
It's comparing it, and this is your comparator. And then if they aren't the same, it's going to push that around.
Right. To make them match.
Make a match.
Yeah. Okay. Yeah. Wow.
Now the beauty of this is because this time constant is relatively long, this will keep the average on this very, very accurate. But we can do short-term modulation with it.
Oh.
See, we can scoot it back and forth with our FM modulation, but it still keeps the center where it wants to be.
Right.
So
And
that's
you said
direct
that because the time.
the time lapse, yeah, we put a time lapse in here.
Okay.
So if this were too short a time constant,
Right.
it would not allow us to correct it because once we try to move it, it immediately puts it back where it's supposed to be.
Right. Right.
So it allows us a little slop there to move the frequency, but on the average, it keeps it where it's supposed to be.
Okay.
So we have to be very careful about these time constants, that sort of thing. So we talked about time constants very early in class. This is one application where that became very, very important.
Time constants, yeah.
But this is your basic phase lock loop, and it's used everywhere now. I mean,
And that does what now?
well, what it does is allows us to lock a free running oscillator to a reference. Now,
A lock, yes.
yeah. Now, how do we do multiple frequencies? Well,
Right.
what we do here is this frequency doesn't have to be the same as this.
Right.
if we want this oscillator to be 2 megahertz, what do? We let the free run at 10 megahertz, but then we use a frequency divider here.
Really?
So now we take a frequency divider. Did I say 10? Let's say the 2. Let's say we want this at 2.
Okay.
And so we use a divide by 2 circuit here, which takes whatever this frequency is, which is a sine wave, divides by 2 first,
Yes.
and then have it. So then what this will do is it'll phase lock to this frequency so that
To 2.
yeah.
Wow. Yes.
So then all we have to do to change frequency is change what we call the modulus. We change the divising factor that we have. So we can take any number of dividers on here, divide this thing down, and then we lock it at what the divided down frequency is.
Uh-huh.
It's
Okay.
like, okay, so this is how you do fast frequency changing. Now on a cell phone with the frequency hopping, it's doing this, changing this modulus continually. It's just zipping all over the place, changing what the division ratio is. But to keep it sane, it always keeps the phase lock in there.
It does. Oh, are you going to get into the internals of that, or not, of that divisor?
Oh, divide by 2? One divide? Okay, we'll do divide by 2.
I mean, okay, yeah.
Takes 2 transistors.
Ah,
So now we're in the digital domain.
I see.
I see, very good, I see.
Is it? Okay. So you need transistors. Probably lots of them, huh?
Maybe we'll spend one class building a phase lock loop. That sounds fun.
Fantastic. Yes, it does. So do you need matching hardware for every division that you do? Or can you have some
Matching.
variation? Well, yeah.
So, fundamental memory unit.
Okay.
Every memory device on the planet is built around. Called a flip-flop,
Of course.
of course. And it takes 2 transistors. Or tubes, like in the old days, they did it back in tubes.
Wow.
So back to, okay, so
Oh, wow.
2 load resistors here. And we have this one goes over here.
Those are all
Okay.
resistors.
And this is our DCC, which remember means common collectible. Okay,
Uh-huh.
so you have 2 transistors cross-coupled like this. So if you first turn this on, this transistor is on, this voltage here is going to go down, right? And if that goes down, this transistor is going to go and turn on. So if this goes down, this transistor is going to turn off. Which
Okay,
means this
sorry,
voltage.
start it over again?
Okay, we start on, let's say this transistor is just conducting slightly more. Again, this requires a certain amount of unballast to start with.
Okay.
If this transistor first starts conducting,
Yes.
right, this voltage at this point is going to come down to 0. Because this transistor turns on, and now we have a voltage divider between here and here.
Oh,
So it's going to turn this voltage off.
okay.
This voltage being off is going to turn this transistor off.
Hmm.
Which means this voltage is going to go fully up.
Oh,
Now, if that voltage is fully up, that's going to give positive reinforcement.
yes.
That's going to turn this on harder. And so now, if we were to force this thing to switch states, all we have to do is put a positive voltage on this guy here. No, put a negative voltage on this guy.
Negative, okay.
That'll turn this transistor off, and the whole process will reverse. So we turn that off, turn that off, this voltage will go high, turn this on, and then bring it back low again. So it's positive reinforcement in one state or another, because bistable. It's a toggle switch, okay?
It is.
It's toggle, yeah. So it's a bistable,
Wow.
bistable, which means it's, it can only stay in whatever state you force it. So if this starts in the on state and we give this a negative trigger here, it always reverses. So these 2 points here are our outputs, and we can call them Q1 and Q prime, or Q and Q prime.
Okay.
And they're never going to be the same. When one high, the other one's lower, and vice versa.
Okay.
Now,
Wow.
we can either force this with 2 different signals. We need 2 switches, one to turn this one on and then one to turn this on and toggle it. But
Right.
actually, that digital thing there will do that for you. But if we want a single pulse triggering that, what we do is we take this input here and the diode. Put a diode here, and we also put a diode here. And then this could go to our negative pulse generator.
Okay.
So, if this is already at a low state, if we hit a low voltage on here, that diode's not going to conduct anyway. It's not going to do anything. But it will force this guy to go low. Okay. So whichever one is active, that's not going to respond to the pulse. So if we send a pulse, every time we send a pulse here, this is going to switch states. So I send one pulse here, this will go high, that will go low. Send the same pulse through here, that will go high, and this will go low. So we toggle the states here with a single pulse there.
Yes.
If we don't have the diodes in there, then we have to force it on either side. We have to use 2 different switches, one to switch it up and one to switch it
A
down.
pulse such as a frequency from a
Or it could be
RF.
Or it could be RF. Well, you want to convert the RF into digital to start with.
Right.
So,
Okay.
but it's actually if you get down, it's actually just the leading edge of a pulse that does it. Called edge detection. So we talk about some of the more fine details of it.
Wow.
But basically, it's 2 transistors cross-coupled, so they got positive feedback. When one turns on, the other one has to turn off, and vice versa. So they're always going to toggle. So now, if we were to look at just one side or the other, we can look at either one. That's going to change states every time this has 2 states to go through, right?
Yes.
And a pulse here changes to 1. This goes to 0. This goes to 1. The next pulse is going to be 1 and 0. So what it does is we get a positive pulse or a positive state for every 2 pulses here. So it's a frequency divider. So this will give us, if we were
You just divide it by 2.
just divide by 2.
Okay.
If we want to divide by 4, we just take 2 of these and cascade them. If we want to divide by 16, we take 4 of them and cascade them. Okay, that's your basic logic, memory logic component of any computer. So if you got a RAM memory,
Wow.
so you got.
What do you call this again?
That's your flip-flop.
Flip-flop fundamental memory unit.
Yeah.
Wow.
So you got RAM there, you got just millions and millions of those.
Yeah. And that's how you can divide by
Divide or store. This is your fundamental data storage.
storage.
Because at least toggle it stores a 1 or a 0.
Right. And so that's what's happening in going back to radio and the what we were doing before.
Oh,
Phase lock
yeah.
That's these play into that and
Yeah.
you have more than one.
Yeah, more one. You just pick as many as you want to divide the signal into 1.
Wow. Okay.
Phase lock loops are really cool.
Wow.
Now, another thing nice about a phase lock loop, if you use the receiver, it also acts as a discriminator because
Okay.
So let's say we have a reference oscillator and the talk going of all the gyrations there. Let's say we just have an FM receiver tuned to 1 frequency, so we have a fixed frequency on let's say 100.3 megahertz. Okay, that's a standard FM frequency.
1.3. Okay.
And that's our crystal oscillator. That doesn't change, okay? And we're not going to change anything. All you want to do is take an incoming frequency of the same frequency and demodulate it. So, first thing we do on any of this stuff to make it digital is we go through a comparator. So now we have a square wave coming out. Okay? 100.3 megahertz square wave. we have a signal coming in off wherever it may do the same thing, right?
Okay.
Let's do it better. Let's take a free running 100.3 megahertz oscillator.
Oh,
Okay, and we do the same thing. We go to comparator here, and now we have a square wave coming out there.
uh-huh.
Now we go into our AND gate comparator, right? Or that thing
Right.
adds in. And now we take our integrator, which figures out the average duty cycle of this, depending if they're close they are together.
Okay.
And we,
Huh.
we go back to our voltage controlled oscillator to keep that on the same frequency.
Yeah.
We tap off there and amplify. That's our audio right there.
Right.
The feedback is going to be exactly
Feedback.
proportional to the frequency deviation. So now we can just amplify this feedback, and that's our voltage. That's our audio. Perfect discriminator.
So you just tap off of that
Yeah,
and start amplifying.
an audio amplify, yeah.
Wow, it really is the audio.
Yeah.
It's just the deviation of. And the capacitor there is to do what?
That's what gives you the average. This circuit here is integrated. That's,
Oh, yes,
that's what allows
right.
you to give
Right.
you that DC voltage out of the square wave.
Wow.
It's so simple, but it's so simple to do it. Well, actually, World War II, they were doing phase locking with radar, so I think it's totally against it.
Wow. Again, that first device after the oscillator, what is that?
Oh, that's a comparator?
Comparator.
Yeah.
Why does it have the same symbol as a?
Well, it's just an op amp without any feedback.
Oh, that's right.
You're
That's
using
right.
it
That's
as a
right.
linear motor, just using it to
Yes.
compare the voltage between two. If it's
That's right.
one higher than the other, goes fully up, if lower than the other.
Right. Okay. He just showed it. There's just so much information there. It's like, okay, wow. So that comes out as the frequency of the audio. Yeah.
Have you written any comments yet? No, just to have somebody say, couldn't see it with the light, with the fluorescent bars.
You did?
So that's, no, nothing today, so.
What's the channel called?
It's just a KL7AJ GROL class.
KL7AJ. General what?
GROL, General Radio Operator, General Radio Telephone
There
Operator
it is.
License.
See if I can find it. Well, I guess I'll look for it later. It's not showing up. Okay.
It's on YouTube. Yeah, I'll be sure to
Yeah, sure.
email you guys over. Okay, so we got an AM, FM, we got the slight difference of phase modulation, which result is the same. You can make a phase modulated signal look the same as an FM or vice versa just by using the frequency filtering at the end.
Okay.
Again, the apparent deviation of a phase modulated signal increases with the audio frequency. So it has a built-in pre-emphasis, which is an increase in high frequencies.
Okay.
Okay,
Wow.
let's see, you got phase, lock loop, got transmitters, where can you, what can you do about it? Well, yeah, this same technique can be used in transmitters too. In your cell phone, obviously, you're doing the same thing with your transmitter as well. So
You are.
it was first developed in receivers, but let's see. A lot of modern equipment now use a lot of much of the same circuitry for a transmitter as the receiver. So you don't have to duplicate stuff there. So there's a couple of tricks they use for, I guess amateurs were the first ones to do it, where you use, for the transmitter, use a super heterodyne scheme for both transmitting and receiving.
Huh.
So rather than going frequency multiplication, we used mixing products. So you had an IF, which is also the same for your transmitter frequency. I guess we can go into crystal filters a little bit. Now, we mentioned that a crystal has an equivalent circuit, right?
Yes.
So it looks like a series circuit with a lot of inductance, a teeny tiny amount of resistance, and its capacitor here is your holder capacitance, which is those two plates that you put together there, because the crystal itself is non-conductive, so you just can't stick some electrodes on it and make it do anything. So you have to capacitively couple that energy into that. But since this is a circuit, we can use a circuit as a component of a filter. Now, there's different configurations. One of them called a ladder filter, one's called a lattice filter. But let's talk about a single frequency filter. So let's say we have I have actually, it's in my cabinet there. I have an old receiver there that actually has what's called a crystal phasing method. But what that is it's built into your IF stage. We talked about as you lower the IF frequency, the more selective you can get. We're trying to separate some very closely spaced stations. And what happens is you can only make the Q so high. Well, the crystal, we make this Q razor sharp. So what we do is we put a crystal in there, operate in the series resonant mode. And since a crystal is a series circuit, how does it behave? Well, we know that at the frequency of resonance, it looks like basically a piece of wire. As we move away from that resonance, it goes away. So what we now have is an extremely sharp, high Q IF filter inside our radio. So then, as we tune across there, we just razor sharp tuning. Now, that's really useful for things like CW, Morse code, where all you have is a carrier turning on and off. Okay?
Right.
If you have a signal like a single sideband, where you have a wide range of frequencies, or at least a relatively wide range of frequencies, for most of your voice communications, like we use here, it's between 3 and 3 kilohertz. So it's only like 2700 hertz wide, not like high fidelity audio, but that's all you need for voice. It's standard telephone type quality. So you still want to be able to pass within that range of frequencies. Pretty flat there. Okay. Now, if we look at the response curve of a single tuned circuit, we make a very high Q. Okay. We have a bell curve, right?
Right.
Which is not great for voice. Okay. We have one frequency range there, and even if we broaden it out, it's not uniform across a bandpass. Okay.
Oh, yeah.
So we want something that's relatively uniform across the passband that we want, but we want to drop off very quickly at both sides. Well, the simplest way to do that is to use two tuned circuits that are actually tuned the same frequency. Now we can demonstrate this, but if we take two tuned circuits that are magnetically coupled, and these are both tuned to the same frequency. This is a technique used in just about every AM broadcast radio there is. The IF frequencies are double tuned like this. And they usually have a tunable slug in there. I might have one. So here's a typical 455 kilohertz AM IF slug. Now it usually has a can around the top of it to shield it, it goes like that. So,
I see.
Yeah. So here's the actual can for that. So you have two coils there that are coupled together, and it's got movable ferrite slugs there, so you can change the degree of coupling between them.
You can.
Yeah. There's slugging tubes from both sides, tubes from the bottom and top. Or tubes from both top with, or what kind of.
And that way. Check that out.
Yeah, let's see if I have a proper tuning slug for that. Now, it used to be the job of every radio technician on the planet spent most of his time twiddling those coils, you know, it's just the way it was.
And again, that's AC current going through there?
That's IF, intermediate frequency.
Okay, IF, yeah.
455 kilohertz. So,
Yes. It's gotta be, yeah.
that's right.
So 2 adjustments to get it
Yeah.
close to resonance or a little bit.
Actually, so what, now this is designed so you could go completely through the top and get only the bottom one. See, the
Oh, I
top
see.
there over here, so if you couldn't get to the bottom, you could tune them both from the top there.
Oh.
So every electronic tech on the planet had one of these, or a whole collection of them, so.
Yep. Neat.
So what you do here is by adjusting these 2 slugs together, you change the effective coupling between those 2 coils.
Yeah.
Now, these have a fixed capacitor on each side. Actually, they shouldn't be variable.
Okay.
Yeah, these are fixed tuned.
Oh.
Okay? So these will be tuned to 455. And what you do is you adjust these 2 slugs in the middle. And the closer they got together, the tighter the coupling would be.
Ooh.
And what happens is
What are the slugs made of? Steel?
ferrite.
Ferrite.
High permeability ferrite.
Uh-huh.
Take 2 tuned circuits that are barely coupled, very close to each other. The overall response is going to be the same as one of them. Okay? As you get closer together, you start getting a double hump response like this. This starts separating into 2 different humps like that.
Oh.
Now, 2 things happen. First of all, it's broader in between, but the slope of this line on the outside is steeper than it is in individual tuned circuits,
Is it?
which is what you want, because what you want is you want to obtain all the bandwidth that you want, but you want to very abruptly get rid of what you have out there.
Wow.
So by using double tuned circuit like that, you can achieve that to some degree. Now, as it turns out, the more tuned circuits you have closely coupled, the closer you can approach that ideal brick wall filter in there.
Wow.
And so what you can do here is, I don't have any shock with that. The Collins mechanical filters actually had the equivalent of like 15 of these tuned circuits coupled there. And they use mechanical resonators to do that. So what you do is when you do multiple pole filtering, you have a band pass that has a lot of these little ripples in it, but they're very shallow, okay?
Uh-huh.
The fewer poles you have, the deeper the ripples are, but fewer of them. So if you can have an infinite number of filters, you have a bunch of infinitely small ripples. But you can also have a straight vertical slope on it, which is really what you want to achieve. Because that allows you to put 2 stations right next to each other without slopping over,
Oh, I see.
which is ideal for communications. Now,
Then you just gotta read those ripples.
that's right.
Yeah.
Well, they call those mechanical filters, and that was a major step ahead of time. Somewhere in between,
Wow.
we came with a crystal lattice filter. Now, this is really, really cool stuff. Because this crystal, because you have this holder capacitance, can act as either a series or a parallel resonant circuit.
Huh. The crystal?
The crystal itself. You got the mechanical resonance of the crystal, but you have the holder capacitance too, which looks like it's in parallel with the rest of them. So the crystal actually has 2 resonant frequencies that are pretty close to each other. One's a series resonant, one's a parallel resonant. We can actually measure that. So what happens is if we actually look at the resonant curve of the crystal as you're crossing, that's something that looks like this.
Huh.
Now, what's really slick, let's take 2 crystals and shave one a little bit higher than the other one, okay? And what we do is we adjust it so that the series resonance circuit of one corresponds with the parallel resonance circuit of the other one. And we combine the two waveforms, and we can stagger this one a little bit here like this. Now, if we take that at any point and we add those two together, the algebraic sum is going to be almost a flat line between here and here, which is what we want. Okay, so we stagger to them. So, and the way you do that is pretty basic too. You take one crystal here, you take another crystal here, and let's see.
What's that going to? What are the
That goes to ground.
Is there a resistor there or something?
No, that's just a
Okay.
Okay, here's our input signal here.
Wow.
And if we adjust these values right here, that's going to give you a composite signal, which is going to look almost like that.
Wow.
That's called a half lattice filter, and every decent ham radio transmitter and receiver that's not worthy of its name had something like a half lattice crystal in there.
And that's some fine tuning of those crystals.
Yeah.
And then you have to do the mathematics or whatever to
Well,
know
that's
what
pretty
the what the overlapping.
Yeah. So it's usually designed to optimize around 2.5 to 2.5 kilohertz difference in.
Oh.
That's why every ham had piles of crystals like that.
Piles.
Piles of crystals.
Because each. Oh, it didn't have just two. It had.
Well, no, this circuit only has two.
Right.
They have to be properly matched, so.
Yeah. And so why does the ham have piles of circuits?
Well, this is all done in his basement.
Right. Oh, right. Yeah. Wow. So the series frequency and the parallel frequency are different.
Yeah. Now, if we want to take advantage of this parallel frequency, we could use that as a notch filter. You put it in series with the circuit. We want to get rid of one frequency. There's a case for doing that when you have a lot of interference and you have a specific station that's interfering. And that happens a lot when you have like amateur radio communications mixed in with shortwave broadcasting. So these really high power shortwave broadcasting has a carrier on all the time, and you want to get rid of that carrier. And you would have pretty much the same sort of thing. You have an IF amplifier, but you'd have the crystal would be between there and ground.
Wow. Huh.
But rather than being in series or glowing. So what happens is at the resonant frequency, or the frequency that's interfering with you, that it goes, basically looks like it's short to ground, so you short that out.
Right. And that it's not quite your frequency, but it's close enough, and that's why it's
Well, yeah, well, you could, but because it's a super head receiver, when you adjust your main tuning, you're actually adjusting the frequency of this incoming signal.
Wow.
So,
Like a force field.
yeah, so you're actually, you have the IF, which has a certain bandwidth, but there you can, remember the IF frequency is the difference between your local oscillator and the incoming signal. If you're adjusting the local oscillator frequency, the incoming frequency is going to change. That's why the pitch changes on a signal sideband as you tune across it.
Yes. Wow. Okay.
Let's see. Put it on the air here and demonstrate it.
And so again, this would help you separate two different.
Well, it's helping you reject a particular station that's interfering.
It's interfering.
Yeah, so you can just lop it right out.
Right.
Lop it right out.
But it's nearby. But you.
Yeah, it has to be close enough.
Chop
It
it off.
has to be somewhere inside the IF passband.
I see. Wow.
What is that? Does that only chop it off as would be seen on yours, or does that chop it off?
No, just on your, that's your
Just on your
receiver.
side.
Yeah.
And you'd need a new crystal every time you,
Well, no, because that's the beauty of having the IF frequency is because you just tune your main tuning there.
oh,
When you tune your main tuning, it shifts everything into your IF frequency.
for the crystal.
Yeah.
Wow. Okay.
All you have to do is play around with it for a bit.
Right.
Get yourself a shortwave radio. You got plenty
Yes.
of money now. Just
Yeah.
see how that works with it.
Wow.
Now, since we did mention CW, which is simply an on-off carrier keying,
Uh-huh.
we have to have one ingredient in order to be able to hear it, right? Let's say we have an incoming signal.
Mm-hmm.
I'll pick 7 megahertz since that's an amateur band very commonly used for. And we have an RF amplifier, and we have another RF amplifier. Then we have a detector. And remember an AM detector, all you need is a diode to lop off the top or the bottom half of it.
Mm-hmm.
You do that with Morse code, you're left with nothing. Because there's no information on it. It's just a carrier that's either there or not.
Right. Oh,
So
yeah.
how do we hear a Morse code signal there with a carrier? Well, what we have to do, since that carrier, even if we have a bunch of IF conversions there, it's still radio frequency, okay? How do we get down to audio frequency? Well, you need another mixer down here. And then this mixer, rather than having a local oscillator, which is, up in the radio frequency, this is basically just a difference between this. So let's say we have a 50 kilohertz IF.
Okay. And that was
And we did-
7 megahertz up there?
Yeah, so 7 megahertz, and we've already converted this down to
Down,
50 kilohertz.
Okay.
So we'd have this like 51 kilohertz, okay? So that would mean when we have a carrier on here, we get a 1 kilohertz tone, which is audio frequency that we hear.
Right.
This is called your BFO in this case. It's just another local oscillator. It's called beat frequency oscillator, and that's what allows you to actually hear a CW that doesn't have modulation on it.
Right. Just a
When we're listening to single sideband, which also needs to have a carrier re-injected, this is now evolves to what's called a product detector. Because on single sideband, you don't have a carrier to help you demodulate it, so you don't have the complete thing. See if I can find some undemodulated single sideband somewhere here. Bands have been really horrible lately, so seems like some years.
Could it be the sun activity?
Oh yeah, the sun's been blowing shunts.
That's what I hear recently.
It's gonna knock out the internet.
I hear we've had like some of the largest ones ever, if not the largest. Flares. It's yeah, Nicholas. Not Eric Nicholas 1352. Thanks, man. Yeah. You just looked at the name or you saw it up there or what?
No, I just looked it up.
Cool.
Just search for all options.
Good deal.
I was actually watching this one.
You been watching it? It's actually cool. There you
There's
go.
a bit of a delay.
Well, there's a couple Eric Nichols on here. It's 3252.
Still pretty miserable out there. Sometime in our class we'll get some no propagation. Anyway, this is your fundamental CW receiver. Yeah, let's see what else say about transmitters.
Subscribe to that.
Oh, going back to audio amplifiers, we talked about how how push-pull amplifier, you amplify top and bottom separately, and we were using transformers for the user high power. Talk about the output stage of those op amps a little bit. We use, and this can be used up. This technique can be used at any power level. But, remember what we call this particular circuit here? Ooh. got transistors at.
It looks like they're flipped.
Yeah, well, a little bit more than just up there.
PNP versus NP.
That's right, this is an NPN,
Is it?
yeah, this is PNP.
Is there something that showed us that?
Yeah, the direction of the arrow is in the
The
transistor.
direction of the, yeah, okay, yeah. That's what I thought, okay.
Okay.
Ah,
The current always flows against the arrow. Anyway,
Right.
this one here, without having to have any transformers to flip the polarity so you can amplify the positive negative peaks, these will do it automatically because the polarity of the transistor is backwards. So with the same signal, let's turn this one on, we'll turn that one off. So we can just come into here with a input signal. And
Okay.
that'll do our phase inversion automatically.
phase inversion.
Yeah.
To,
This will amplify the top, and this will amplify the bottom.
oh,
But at any point in time, none of them are both conducting, and that gives you a lot more efficiency because when one's working, the other one's resting. It's a Class B complementary amplifier. We're using complementary transistors.
wow.
And the output, remember we looked at the schematic of the 741 op amp? Well, that's the output stage of those.
Yeah. Wow.
And it greatly simplifies it, because there's no vacuum tube equivalent of this guy. You've heard of CMOS memory, computer stuff. I
It's
just
been a
memory
while.
called CMOS.
CMOS?
Complementary metal oxide transistor. So you actually have each gate has both a PNP or the equivalent. It's actually an N gate FET or a P gate FET. So FET is the nickel, and MOS means metal oxide semiconductor, which is a field effect transistor, which works a little bit different than these. But they have complementary pairs too. So you have one that turns on with a positive voltage, one turns off with a positive voltage. So anyway, for high-powered audio amplifiers, and 99% of your high-powered solid-state amplifiers have complementary output
They do.
transition. Yeah. So you get matched pairs of PNP and PNs. You get to do that. You greatly simplify the circuit design because you don't have to put transformers or anything else in there.
Yeah.
Now, there's a couple other ways of doing the phase inversion necessary to do that. Again, you need a phase inversion to tell one to conduct and the other one to shut off. And a couple ways they used to do it in vacuum tube amps. Some of the older vendors still, or more modern vendors still do it. It's called a split load phase inverter. And say we have a vacuum tube here, and we have a load resistor up here. And then we also have, here's a grid, here's a cathode here. We have a load resistor down there. Now, if we put input signal in here, what happens to this voltage? As we increase the voltage on the grid here. This tube conducts more, so you're going to have more current through there, so you're going to have a greater voltage drop. So this is going to come down.
Voltage drop. Okay. Oh, right.
This is going to do the same thing, except because the tube is on the top side of that, this voltage is going to go up. Okay. So a single input signal is going to give us two output signals that are out of phase. So it's called split load phase inverter.
Okay.
And this would be bias class A. Let's see. So this tube is always conducting. So it's not a high efficiency amplifier. Its only purpose is to give you two signals that are out of phase without having to use a transformer. Anytime you have a transformer in iron, it's very expensive.
Oh.
So then you couple this off here.
So either one of those sides is
So
conducting.
one will be up, one will be down at the same time.
And they're both connected to ground, is that what you're talking about?
Well, that's relative to ground. Whenever measuring any voltage is always talking about potential relative to ground.
Oh. Okay. Wow.
Now here's something interesting. You can also do it in transistor. Now, you remember when we first built our little amplifier?
Yes.
Okay. And
Right.
okay, what was it? What determined the gain of that amplifier? How did we determine how much gain we got out of that stage?
We had a,
Very simple formula.
oh. It was the ratio of, yeah,
Okay.
the, E and C.
This
Right.
ratio of R1 to R2. Okay.
Oh, right.
What if
Okay.
R1 and what are R1 and R2 are the same value?
Then there's no gain.
That's right. So it's unity gain. Okay. If R2 equals R1, that means that the output here is going to be exactly the same output here except out of phase. Okay.
Okay.
So we have no gain from the input. We have zero gain on the input. That's called this is actually a voltage follower on the input there.
Huh. Okay.
Isn't it cool?
So this is going, oh, wow, okay. Yeah.
Since it has no gain, it's the only purpose this thing can possibly have is for phase inversion. It doesn't do anything else for us. So
Yeah. Wow.
it doesn't matter what values are, if they're the same, we get no gain out of that.
Can you get a wave out of that?
Oh yeah, that's what you can get. It's a very perfect reproduction wave you have going in.
I'm just
There's
saying
just no
because,
amplification.
because it's an on and off transistor.
No, it's not. No, this would be biased Class A. So we would adjust this to get our half our supply voltage at that point, just like any other.
The voltage would go up and down.
Yeah.
Depending, oh, okay. Okay. Oh, there's transistors like that.
Remember, that's the definition of Class A is linear, which means it
Linear.
amplifies the entire input signal.
Okay. Before we were dealing with not a Class A.
Well, the Class C is the power amplifier Class C, where you're only sending the pulses through.
Yeah. Okay.
And where you have exactly half of the wave, that's Class B. So A is a whole wave, B is exactly half, and C is anything less than that, like the Class C amplifier, RF amplifier.
Mm-hmm.
But Class C is only used with a tank circuit. It only works at one frequency.
Mm-hmm. Wow. Okay. What's that called?
That's called a Class A phase inverter, or split load phase inverter. So you just, yeah, you just split.
Right. And since it's out of phase,
Mhm.
why are we doing that?
To drive the next stage where you need a push-pull amplifier. So
Oh,
we
wow.
use that to get, this would be an intermediate stage before you go to the final amplifier where you need one turning on and the other turn off. Otherwise, you need a transformer, or another transformer. You need a transformer anyway in output. But iron's always expensive. Anytime you can avoid iron in the
Oh,
amplifier.
wow. Okay. And so are you getting just one half of the,
No, in this case,
out of phase.
you're getting the complete wave.
you are, on both sides,
On
it's
both
just
sides.
out of phase, and then you, okay. For push pull.
Yep.
Okay.
I'll find an old Fender, and that's, next time we get a Fender amp here, it'll have the split load phase.
And how much out of phase is it?
Exactly 180.
It is?
Yep.
Okay. And you would want that to be 180, why?
Because you want to drive one tube positive when the other one's off.
Oh, right, you'd want to turn one off and one on.
Yeah.
Okay. Yeah. Okay. Wow, all these are just, gee,
That's on your Fender certification exam, by
I bet.
the way.
I bet. That would be.
Now, that's not the only way of doing that. That's a very, very simple and standard one. Another one is a differential amplifier, which is also the front end of your op amp, if you remember that. You can do that with vacuum.
That was called a what again? And some
This is just a split load phase inverter.
split loads. Yeah. just with one transistor, Class A transistor.
Now, this requires one more tube to do this job, but it's wonderfully. Okay, so. Okay, that should look familiar because that's what the front end of an op amp looks like, or the differential amplifier.
Mm-hmm.
What do we have here?
What do we have there?
Vitamin K, yeah, what do we call that?
Vitamin K? What do we call that? We call that...
K from the determined guy. It's a node.
A node, okay, all right, yeah.
And
all right.
what do we work, when we talk about nodes, what rule applies?
Kirchhoff.
Kirchhoff's current law, okay? So we have a very high value of resistance here.
Okay.
R is very, very high. As we draw more current through this tube, what has to happen to the current in this side?
Go down.
Can go down.
Yeah.
Okay. So we have a differential amplifier. And what this actually does is gives us two signals that are out of phase.
Opposite, that's phase.
Yeah.
So,
Now the advantage of this one, you actually get some voltage gain, unlike the split load where you don't have any gain.
right,
This you can get voltage gain.
voltage gain. And what's the C again?
That's your bias voltage. A, B, and C battery. The A battery is your filament, the B is your plate voltage, and the C battery is your bias. Going back to really early nomenclature, when every radio had to have 3 batteries to run the thing.
Wow. So, and then your, okay, your IF is coming in, and you only have to go
Well,
up to one.
this is audio. This is not good.
Okay, your audio is coming in, right,
Yeah.
okay, and it only has to go into one of those tubes,
Only one of those tubes, yeah.
because if that's on, then that means that's on,
Yeah.
and if that turns off.
Now you can actually run in both of them, and then this amplifies the difference between the two voltages. And that circuit's used for really super low noise applications.
Ooh,
I've never seen a guitar amp use that, but for
Right.
other.
and then there's resistors on the other end
Yeah.
to do what?
Well, you need a load on here for this thing to work, so the output's
Oh.
coming in here, so you can take one or the other. Or both.
Oh, right. So okay,
So this gives you a differential output with a single-ended input, or a differential input. You can use either one.
wow,
Ideally, this thing here would be a fixed current source,
fixed current source, okay.
constant current source, which is symbolized like that. But a high value of resistance also gives you
Gives you,
close to approaching.
and then those tubes are class
Those are all both in class A.
A, because they give you the full, okay, yeah. Whew. And what is this called?
That's called a differential amplifier.
Differential amplifier. That's probably also on the pen. Maybe, I don't know.
Now,
Are they using these anymore?
oh yeah, a lot of Fender amps have them. Marshalls use almost exclusively those. So. Now, in the back of your car, if you got an older style car, you got this thing called a differential, right?
Mm-hmm.
And the drive shaft speed is the difference between your right and left wheel, right?
Yes.
So they used to build mechanical calculators using mechanical differentials to do stuff.
That's cool. Yeah. The drive shaft speed,
Well, it's
based
actually
from
yeah.
the base.
Yes, if you lock one in, the drive shaft's gonna go the same speed as the other wheel there, so if you spin both your wheels the opposite direction, the drive shaft won't be spinning at all, right?
Right. Right. Huh. They just did that with different gears and,
Different gears, yeah.
yeah.
Remember, you're old enough to remember the reactor sets.
Oh, yeah.
I used to build differentials with the reactor set, and the motor thing that you built. I was a weird kid. Look at it with my reactor, oh, let me build a differential.
Yeah. I'm gonna have to open one of those up. I've got a parts truck that I'll have to, yeah.
So does the concept of AM modulation itself make sense? And how the sidebands all work? And
Yes, it does.
you will be tested on that.
I'm sure.
Yes. There's a next week. We are not meeting. Next week in 2 days, Kevin Abnett's going to be here and he's going to talk about transmission lines. So
Is he? Have you talked to him recently?
yeah, I just talked to him today. So
Oh, yeah, I heard he was sick.
oh, he didn't,
He didn't say anything?
I didn't say anything about that. So
He's probably okay. I got to do the class. So he's gonna talk about transmission lines.
yeah,
Fabulous. That's it, Tuesday.
that is
No,
Thursday.
Thursday.
Yeah.
Oh, because we're skipping.
Next Tuesday, yeah.
Great. Awesome.
Mystery components in here. There's a local oscillator.
Is it
Local oscillator coil.
coil? And it can be adjusted?
Yeah,
Right here.
that one. Yeah. It's from a TV, I believe.
Wow. So, okay. Well, check it out. Those are the only two. Okay. Oh, and there's a ferrite
Ferrite slug in there.
plug in there that comes in. Okay. Wow.
Any comments here? No comments yet, huh? Okay. No. I'll have to promote my site more. Then I can start monetizing it too. You have to have 500 subscribers. So you know 500 people.
Right, I might.
There's
You
two
know 500
subscribers
people,
so
and then I
far.
start getting paid to put this thing on the air here.
Just gotta pay $500 for 500 people, $1 a piece.
Well, it didn't. There's no monetary value there. What in order to certainly does it for YouTube. It's one main company that does that, and then they
What do they
do a
do?
sort and they say, hey, is this advertising suitable for your program? You know, and then you get
Oh.
pick and choose what you want there. But they don't
Okay.
start the process till you got 500 subscribers. So
I wonder who it is. Yeah, I mean, you'd really only know if you have a channel. Who the advertiser is, who the...
oh, well, it's one. I forgot the name of the
The
company.
media
It's,
company.
yeah, it's kind of the conglomerate,
Conglomerate
the collector, what do they call
of
it?
aggregator
Aggregator, yeah.
of
Of advertisers.
ads,
Yeah.
advertisers. Yeah.
Yeah.
Interesting.
And then, it'd be a good thing, nice little perk there. We'll send them to get some more people watching this thing. You know?
Yeah.
Why don't we make some
Have you ever seen? You want to see a great guy? Guy does pretty well. I guess pretty regular. Mr. Carlson's Laboratory. Look that up. That is an amazing show. So he goes to those old antique test equipment and takes it apart for you and puts it together. Another one, if you like, really a lot of really good historical stuff on technology. Go to Fran Lab. Name's Fran Blanche, and she's has deep connections with NASA, and you know, she knows most of the heavy players, so she's got a really cool program. She likes taking like these old mechanical displays apart, like clock things with Nixie tubes and all that kind of stuff there. So.
Well, and I feel from what you've shown us is that if you can understand what the original design was, then it makes it more intuitive when you're looking at,
Yeah.
you know.
Yeah, that's why I always start with vacuum tubes, because the vacuum tubes are very intuitive, because you're just basically billiard balls, you know. When you get transistors, it's
Right.
Fortunately, you don't have to know how a transistor, you just have to know how it behaves from the outside world, you know. Well, it's all Ben Franklin's fault, you know, because the ancient Egyptians knew about it too. They were doing electroplating. They were. But Ben Franklin, when he was defining what electric current was, he was looking, okay, we've got this electrolytic solution, and he was like taking electroplating copper, so you have a silver bar and I forgot what the copper sulfate or whatever it was, and he was saying the silver was being plated on the copper.
Right.
Said, well, that's the current flow. Well, that's
Sure.
the ion flow, you know.
That's the ion flow.
The electrons weren't known until 100 years later, you know. So considering what he had to work with, he had no clue, you know.
Right.
But the numbers all work out the same because for every electron that moves one direction, you have a hole to fill going the other direction. And so the numbers all work out the same. So you don't have to obsess about are we talking about a current flow or
You don't.
or conventional current flow or current flow. You know. But it's Ben Franklin's fault that the current goes against the arrow in a transistor.
Right.
Yeah, that's the whole flow.
Going all the way back, and we just kept it.
That's right.
It's funny, man.
It's not like you can change it.
Right, you can't switch it mid-year when
That's
half
right.
of your PhDs are already, you know.
Yeah. Well, another thing interesting is, you know, we talk about different velocity of electricity. You know, we have
Right.
we talk about the
Different
electron.
material.
The actual electron drift is a
Slow.
bit abominably slow, except in a vacuum. In a vacuum tube, you can approach a good percentage of the speed of light. You can't quite get there, but you can get, you know, really high velocities there.
Yeah.
So, when you're talking about conductivity in a wire, there's a huge difference between the current flow and
What was it
the
again?
energy flow.
It was like 2 inches per
Yeah,
every hour.
Yeah.
Is that what it was?
Yeah. But in a vacuum tube, though, and what limits the actual high frequency that a vacuum tube can work out, which is why klystrons were invented, is because the velocity factor it takes. So far, we've talked about vacuum tubes. We haven't considered the time it takes for something to happen here and there. But when you get high enough frequency, the time delay going through a vacuum tube could be enough where it won't amplify anymore. Because you're doing this effect here, and the effect doesn't happen until it's out of phase, you know. So they work rather than try to get around that. You can make the tube work at higher frequencies by using higher and higher plate voltages, but then you reach a limit there where it starts arcing over inside, and so there's practical limits to how high the plate voltage is.
Wow.
So what they did is rather than trying to get around that, they take advantage of the grouping. So what they do is they delay the grouping of electrons from the first burst, and then let them bunch up. So they know there's going to be a delay time. Well, they just wait till the next phase of there. So then what they do is they cause the electrons to occur in groups, and then it's the pulses between the groups, it's the actual frequency you're amplifying. So it's like taking a bunch of shotguns and shooting them at the right time, and then measuring the space between the clusters.
Right. And then you can multiply that?
Yeah, you multiply that. Yeah. So that's how klystron works, yeah.
Wow, and you would know by a certain amount.
Well, exactly, yeah, the klystrons have to be precisely tuned, so. Yeah. Look up reflex klystron. It's,
Okay.
Yeah.
Wow.
That's would be a little homework assignment, but I don't know if those are magnetrons here, which are a little more intuitive, but let's see if it's klystron.
Does it? Megatron? Yeah.
No klystrons.
I feel like for the first few years in electronics, you could just spend your time understanding how these different devices work, the designs, and then probably forget it and come back a little while and say, oh, yes, that's right. Oh, yeah. But that's... I mean, you've got thousands of designs, really.
Here's a plan. They don't go a lot into it.
Oh, klystron. And so it would be would that make it like an A class? Or C class,
Yeah, it's,
Kind
I don't
of.
think those,
There's no class.
they don't apply to.
Because it's either on or off, right?
Well, no, it's a true amplifier.
Okay.
It's,
But it's,
the classes, you don't have the bias, well, you don't have a grid, so it's hard to define the biases, you don't have the same elements, you know, so.
oh, it's different.
Yeah,
Okay.
class is very different too.
Wow. Oh, all right. Got it right.
Yeah, it's got there's reflex flytrons and non-reflex. The reflex flytron is used as an oscillator, and the non-reflex is used as an amplifier, so.
Absolutely.
Okay, well, I guess I will
Thank you.
probably not be seeing you until,
A week? Well, I might see you tomorrow. I'll probably
Yeah.
see you
Oh,
tomorrow.
that's
I'm
right,
gonna
that's
try
right.
to make it to that. Let's see.
until the next year. We'll see you.
That's right.
Before I see you again.
Is it? Wow.
Yeah.
Happy New Year.
Well, same to
Merry
you.
Christmas. Yeah.
Merry Christmas.
Really?
Thank you.
I close, huh?